Hey, what's up? So I'm back with set three of the Cryptopals challenges. I'll give the same little spiel that I think I probably gave in front of the other two, which is basically that this series is kind of aimed at the beginner. I know most people use Cryptopals as a way to either learn programming language or cryptography or both. So I'm doing these challenges in Python 3. I am not an expert in either cryptography or Python 3, but I feel like I know both well enough that I can go through these and hopefully explain it, and somebody who is a beginner will get something out of it. I've looked through these, so I kind of know what's coming up, but I'm just basically going to be like live coding this as we go. I'll be building on the previous code that I made in the previous two challenges. Most people, I imagine, probably get to videos like these because they're searching for a specific problem that they're either trying to understand or they got stuck on. So I'm going to have, they're all time stamped so you can jump right to it. I don't imagine there's probably too many people that are going to be like, well, let's just listen to what this dumbass has to say for the next, I don't know, 5 hours. I think the last one was like almost 5 hours long. So I have no idea how long this one will be. Um, I don't really know much. I don't know anything about MT19937, but I did look, when I looked through, I don't think the actual attacks really matter at all. So it'll be kind of cool. I guess we can learn that together. I think that's it basically. So let's just go ahead and jump in and start going. So this first one, the CBC padding oracle attack, is actually a really cool attack, and it looks like in the same fashion that we've kind of been doing in the previous challenges is we're basically going to build the service that we're then going to hack, or essentially like we'll build the service whose cryptography we're going to break. So it looks like, so these are just base 64 encoded like plain text, so it'll probably be song lyrics like what it's been before, and we're going to randomly choose one and encrypt it and give it back to the user, and then we'll have another function that basically lets us know if there's valid padding. And the reason I like this, the reason I think this is such a cool attack is basically we're not going to, if this was a service that we had access to, right, it's just going to give us some random encryption and it'll tell us if some encryption we give it has valid padding. And from that, we're not going to know anything about the key. We're not going to know anything at all about what any plain text decrypts to. We won't get any information other from the decryption other than whether or not it's valid padding. And from that, we'll be able to completely recover any encryptions it gives us. So the way that's going to work is, if I'll go back to that diagram of how CBC works, just to like kind of go over it. Here we go. So CBC, if you don't remember, is basically the flaw in ECB is that like the same plain text is always encrypted to the same ciphertext under the same key. So now you introduce a random IV, and then each previous block of ciphertext gets XORed into the plain text before it's passed into the AES function. So that kind of like, now you don't have that same problem. And decryption then is just going to be the exact opposite. So what comes out of the AES function is going to get XORed with the previous ciphertext, and that's how we're going to get the plain text. So let me go ahead and maybe put my little thing here. I'll try and explain it real quick how this attack is actually going to work. So let's say we got from the oracle, we got the actual IV, and we got a block of ciphertext, and it's just, we can't tell what it is because it's all random bytes. And then if we look at our diagram, we see that the way AES works is there's a key. The decryption is going to be the ciphertext. This is ciphertext, and it'll be the previous block of ciphertext, or in the case, I'll just explain it with the first block. So we're going to have the IV, again 16 bytes, and it's going to get XORed with what comes out of the AES, which if we remember is called the key stream. So we're going to have these key stream bytes that come out of the AES. They're going to get XORed with the IV, or the previous block of ciphertext, and that is how we're going to end up. That's how you end up with plain text. Now, if we remember, AES works on blocks. So everything you input into AES has to be a multiple of 16, because it has to be chunked up into 16-byte blocks. So when a message isn't divisible by 16, right? So you'll have not enough to fill a block. You have what's called padding. And the way AES works, we've been doing it is with PKCS number 7 padding. So basically, if we're 1 byte short of a block, the last byte in the block gets a 1 in it. If we are 2 bytes short, the last block gets the byte 2 times. If we're 3 short, we're going to get 3 times, and on down the line. And padding is required. So if you were sending a message that was, say, exactly 16 bytes, it would stick on a block of padding. So that whole block would be the byte value 16. There'd be 16 of them. So what's going to happen is, when say this service is, I don't know, our thing, the reason we're giving it a ciphertext is maybe it's part of a cookie, or it's an API or something. And when it decrypts, right, because it's going to have to see, maybe they encrypted the cookie, a piece of the cookie, and that's what holds some important, state variables that'll get used in your session. So it has to decrypt that in order to read it. So when it decrypts, it has to unpad. Well, since we're giving it the ciphertext, like it's a cookie, right? We can put whatever the heck we want into it. So we control the ciphertext and the IV. Like, we control all the blocks of ciphertext and the IV we give it. So like, imagine what would happen if we just gave it a block of just completely random gibberish as a ciphertext and a block of completely random gibberish as an IV. So what's going to come out is just going to be random gibberish. It's going to get XORed with random gibberish, and you're going to get nothing but random gibberish here. Well, when it goes to unpad that, since it's all just random gibberish, it's very, very unlikely that they'll have random padding, right? So like, there's only one time in 256 is this position here going to end with the byte value 1, which would be valid padding, right? When it goes to check, it'll say, oh, okay, the last byte's a 1, that's valid padding. So 255 times out of 256, whatever the program is, and a lot of times this is where you can get a padding oracle attack, because the developer didn't plan for, oh, well, what happens if someone just gives us garbage? They're expecting the padding to be valid padding, because why would you give it anything that they didn't give you, and they gave you what was was going to decrypt to a valid message. So maybe you're able to tell that it's invalid padding by, maybe it throws an error. Maybe you can just tell in the response to the web page because the cookie was invalid, so the state's not what it should be, or what you would expect if it was valid. So what we can do then, and then back to the random. So like, only one time out of 256 squared is it going to end in 0202, which would be valid padding. So basically, we can use the fact that it's never really going to have random, or it's never really going to have valid padding to our advantage. So what we're actually going to do is, like, think what would happen is we're going to give it the actual, like, say we have a real block of ciphertext that we want to know what it decrypts to, but we have no way to do it. But we have found a way via the response to the site or whatever or the service that lets us know, oh, hey, it is or isn't valid padding. So what's going to come out of here is going to be the actual key stream of when that legit block of ciphertext is decrypted. But since, again, we have full control over what's getting passed into it, we control the IV. So, like, again, look what would happen if we just made the IV 16 random bytes. So randomly, anything XORed with the key stream is just going to be random, and we're not going to get valid padding. Well, what if we gave it 15 bytes of random stuff, and then this last position here, we give it every single, we go through, we send 256 requests, and we do every single byte value possible in here. Well, one of them is actually going to decrypt, or is actually going to, when it's XORed with whatever the final, let's actually pretend we can see this key stream. So we got 16 bytes that came out. This is the key stream. One of them, when we XOR that, one of those bytes with the final one is actually going to XOR to the byte value 1. And then we'll be able to tell from the response that this was a contains valid padding. Well, what that means then, since we controlled, like, say, our program says, it halts at byte value 123. And it says, when we use byte value 123 here, we got valid padding. Well, because of how XOR works then, we know that that's supposed to be a 1. So when we XOR 1 with 123, we'll get the actual byte value that is the key stream of the decryption of the message we actually want to know. Well, so now we know, or I'll block it in for we know it. We know what this key stream byte equals. Well, now we want to figure out this key stream byte. Well, so to make valid padding now, we need this to end in 02, right? Well, we know what this byte is, so we can make this byte be the thing we want it to be in order for this final one to decrypt or to XOR to 02. So now we can just move up the chain, right? And we'll start working on this one. We'll do the same thing we did before. We'll go through all 256 possible byte values until we get one of them where when it's actually XORed with this, makes that an 02, and the program's going to say, hey, we got valid padding here. So now we know this byte of key stream. And we're just going to do that the whole way down the line until we have the key stream. We have all 16 bytes of what comes out of the AES encryption. When we have that whole key stream, we know the original IV because they had to give it to us, because without that IV, you can't, it's impossible to decrypt. They wouldn't be able to decrypt what this was. So now, since we have the actual real IV, we can take the real IV and XOR it with the key stream that we now know, and it is going to decrypt to the actual, what the actual plaintext would be of the decryption. So hopefully that made sense. Again, this is a pretty famous attack. So I think they even said it in here. There's like a bazillion blogs you can read that kind of go over it, probably better than I did. But that's basically how it's going to work. So over there, we're just going to say whatever message we randomly got. Let's just say it was 3 blocks and an IV. And we're just going to do it a block at a time. We'll figure out what the last block, we could do the blocks in any order we wanted, but we're going to figure out that we're going to do that same process for each block until we have the entire message. So first things first is we're going to code up the service that they want us to use, or that they want us to make. And I'm going to do kind of like in the other one where I'm actually going to make it like a separate class to just kind of distinguish it as this is a separate thing. It just kind of makes it easier, I think, to hold in your mind what it is that we're actually doing than if we have just a whole bunch of functions written out. So let's call it our class padding Oracle. And I know in the other challenges, I actually We kind of went over like programming to interfaces, and I used like kind of an informal interface to do that. But if I remember right, our interface just had an encrypt. That's all it was. And here we're not really encrypting things. We're just getting something that they're encrypting. So we're just gonna like keep it as a class. And then we will have a random key. So we won't ever know what this key is. And then we'll have our messages, and let's get it from these here. Let me just read this again real quick. And then just kind of go over it. Okay, so it's the fun of watching someone live code. My tip would always be, I do this for like everything, is watch everything at 2x speed, because I'm sure, I don't know, it's just way more efficient, right? It takes half as long. You can watch my crappy 5-hour video in 2.5 hours. And once you get good at it, like, it does not sound fast at all. And actually, like, people talking normal gets kind of annoying because you're like, speed it up. So yeah, that's what you should do. It'll make stuff like this less agonizing. But then we're going to have, we'll call it get encrypted message. Oops. And it's going to return bytes. So we want to randomly choose one of these. Actually, like that. We want to randomly choose one of these and then send it back. So, well, first off, we had our urandom here, so we need to import some stuff. And we already know we're going to want to import our AES. I think I was called it utils. And we're going to need padding. The whole point of this attack. So we'll import our padding functions that we wrote. And if you're just joining us, basically we coded all of these to the exact same kind of like specs, for lack of a better word, that PyCryptoDome uses. So really you could just import these from PyCryptoDome. Like if you don't, like basically you don't, what I'm trying to say is you don't need to use my code if you're just like trying to do these, or trying to like, you're like, oh, here I am in challenge whatever 17 and I want to figure out just how to do this. Like you don't need to worry about going to GitHub and like using my code, because you can just, so like instead of from utils import AES, you'd want to do like from crypto cipher import AES. So you can use, and maybe I'll do that in the after I upload them. I'll go in and input what the imports you would want to use if you're not going to use like my code, because I did it purposely so that like pad and unpad and everything, like it'll work exactly the same as if you were using PyCryptoDome. Which, if you're new to cryptography, is kind of like the de facto crypto package you want to use. So we're going to randomly get a message. So, and we need the base64 decode it. So we'll do base64 decode. We'll randomly pick one of the messages. Oh yeah, that's the other thing. So you're probably like, why is this guy not using an IDE? Basically, since like I said, I'm not an expert or anything, and like as I try and learn a language and stuff, Like I feel like I know Python decently well now, but like now it's probably more of a habit. Maybe I should just start using IDE. But like I find that using an IDE makes it so that I forget kind of, it's so handy that I kind of forget everything. So if I do it in just like a text editor, then it like kind of forces me to remember it. Otherwise, like I find myself like I can't write any code unless I have my IDE, which is not always fun. So we're going to create our AES. CBC. Oops. And then, yeah, so we've gotten it. We're going to randomly pick one. We need to from base64 import decode. And then we need, I'll just import random. And then we created our cipher, and what we want to do is return the encryption of what happens when we pad that message. And padding needs a block size, which is annoying because I think these are lowercase. AES is always 16. Okay, you could pad for other things too. So, and then we need another function in our service that basically is going to tell us whether or not is valid padding. I guess we'll just call it is valid padding, since it doesn't really matter for the sake of this exercise. So bytes, we're going to return a Boolean, and then basically we're just going to decrypt it and see if it throws an error or not. So we need the IV, which is the first 16 bytes of, and actually, maybe I spoke too soon because I don't remember now. I can't remember actually if when you encrypt with, I guess we can look it up. When you encrypt with PyCryptodome, if it gives you back Cryptodome AES-CBC node, if it gives you back the if it gives you like a JSON object or a dictionary with the IV, or if it prepends it to the front. I should make these bigger. Yeah, it gives you, so that would be one change. That's unfortunate. Between my code and the PyCryptodome is the way I did it was our IV is just prepended to the front of the ciphertext. So like here, the IV is the first 16 bytes, and the ciphertext is everything else. And then we are going to create our cipher. We have our key that we don't know, and it is, yes, load CBC, and then we have an IV, and then we're going to try to decrypt. So we'll have to do, we have to put it in a try block, because if it throws an exception, we don't want it to crash the program, we want it to handle it. But what we're going to try and do is unpad the decryption of our ciphertext. Again, we have to give unpadding a block size, and if there is an exception, we will return false, because there was an exception. I guess to be completely accurate, we could handle the exception that actually throws for invalid padding, and check to make sure it is that. But I'm not going to do that because I don't know. I don't want to. So basically, I mean, since we're kind of controlling this, like the only way it's going to throw an exception is if we give it valid padding. But just putting it out there for like what's probably better is to catch the exception you want to catch, make sure it's like we would put accept value error as error, and then we would check to make sure error was actually what error is thrown. I can't remember what we put, like not valid padding or something, and then we would have some, and that would definitely be false. And then if we got some other error that wasn't that, then depending on our logic is how we would handle that. So that is our basically our service that we're going to be pretending we didn't build, and that's just out there in the wild, and we are going to break the encryption it's using. So what we're going to have is our typical main jargon, and we will create the oracle. Because again, like I could try and make this more complicated so it'll be more realistic, like that we were interacting with it, but like, I don't know, there's only, at some point, right, like, I mean, we're not going to like spin up a AWS machine and build out a thing. So like at some point you have to like draw the line and be like, all right, I'm being too perfectionist, which is a big problem I have. So, and then what we are going to do then, let's think. So we're going to have an oracle. This oracle gave us a message. We call it get encrypted message. And then what we want to do is recover the plain text from that. So we'll have something called recover plain text, and we'll give it the oracle because it's going to need to make calls to the oracle and the message that we want to recover. And then we'll print out the plain text because they said that yeah, okay. Yeah, okay. Yeah, because these are just, I'm guessing, song lyrics. So, so now we basically just need to create the function that is how we're going to break this encryption. So it needs to have an oracle, and it needs the message. And what it's going to return is bytes. And I talked about this in the other videos, but like basically when I'm doing the cryptography or when I'm writing stuff like this, I always try and do bytes in, bytes out because it's easier to remember. So without like, oops, my caps lock light busted. Without good reason, otherwise, I'm just going to keep it bytes in, bytes out because it just makes everything simpler. Even though like it may probably be different if we were doing it versus an actual service. So let's see here. The way we want this to work is we need to carve up our message into blocks. So let's say CT blocks, and we'll use list comprehension to create those blocks. So we'll start at 16 because the first 16 bytes of what we pass in is going to be the IV. We want to go to the length of the message, and we want to jump 16 at a time. So basically this I is going to iterate, 16, 32, 48, all the way up until we get to the length of the message. And each time it's going to take, 16 through 32, 32 through 48, and it's going to put those in the list. So now we've got this list here that is the message all carved up into blocks. And then we're going to have plain text, which right now we know none of it. And we know we're going off, where is it? We're going off this diagram, and we're just basically ignoring everything over here because we're just going to send it a block at a time. So we're going to give it what we actually are trying to decrypt, and then here's where we're going to do all our random bytes and stuff like that. But as we go through, in reality, the real thing we're going to, after we recover the key stream, we need to XOR it with what the real previous block was. So we need to, maybe I should make this bigger too for the video. I should have remembered what size it was because I actually got a couple really helpful comments on the last video that told me about sizing. So we know the previous block is going to, the very first block is going to be the IV, which we don't have in our ciphertext blocks because we started it on that because we're going to want to iterate over blocks, so we're not going to actually want to use the IV, but we need to keep the IV in the previous message. So we'll put that there, and then now we can iterate over our blocks. And basically what we're going to do is we want an IV that starts out completely random, and we're trying to discover the key stream. And we need to go, let me think about this for a second. We're gonna have to do it 16 times. But I think I want to do, I'm trying to remember because I've done this kind of attack like a bunch of times, so this isn't like I just learned how to do CBC padding Oracle, which is why I'm able to like actually sit here and just hopefully vomit out working code. We're going to check the entire range of bytes. And then what we want to do, right, is we want to have the IV that we're going to give the service be the, we're going to need the random section, the actual byte we're working on, and then we need to correct for the key stream that we've already figured out, right? Because like I showed in the thing I scribbled out, when we know, say like the final, when we know, say 3 bytes of key stream, and we're trying to find the 4th one now, we need to make sure that what we're giving it for our IV has the correct final 3 bytes that when they're decoded with the key stream or XORed with the key stream give us 040404, because the one we're trying to find is the 4th one. We're trying to make that 04. So each time we're going to have to like correct for the key stream that we already know. So we have to make sure and not screw that up. So we're going to have the IV is going to equal the IV up to the 16 minus I bytes, right? Because the first time we actually want to be, we only want 15 random bytes. So this will go to index 15 but not include it, so it's 0 through 14, which is 15 bytes. Then we want to concatenate to that the byte value, and this is how we change an integer to a byte. And then we want, did I import XOR? Yes. And then we want to correct, right? We want what one we're working on. So the first byte, we're going to want those other bytes we found, oh, yeah, okay, so there's actually kind of a thing here where it's, I don't think the first loop through is, yeah, the first loop through this isn't actually going to count, so it's going to, yeah, well, we'll take care of that in the XOR. So basically, like, let's just pretend now we're on I equals 3, which means we're trying to find the third one, so we need the key stream, right? So we're looking for the third one. We've already got 2 bytes of key stream, and so now we need to make the key stream XOR to the bytes 3. So that's, we're going to use, basically I'm rambling to say what we're going to do is we're going to use the XOR function, and what we're going to XOR is, right, the way to get the key stream to be what we want when it's XORed is to XOR the key stream with the thing we want. And that will be what we need the IV to be in order to get it to be what we want. I'm sure that didn't make any sense. But basically, it's because of the way XOR works. Like if you have A XOR B equals C, you can use any 2 of those to get the other ones. Like if you XOR B and C together, you'll get A. If you XOR A and C together, you'll get B. That's just because of the properties of XOR. So that's basically what we're doing here. We have the key stream XORing with the IV, and we want the plain text to be end in the right thing. So to get that, we'll XOR that right thing with the key stream, and that'll give us what we want the IV to be. So hopefully that made a little more sense. So we're going to XOR it with the key stream, and then because in our XOR function we actually programmed an ability to change how long we want to make it, right? So we're just giving it 1 byte. Actually, I don't think we'd have to do anything because it would automatically make it as long as the key stream, but because I'm not entirely sure that my logic is sound, we're actually going to specifically tell it that we want to XOR to the size of the key stream. So it's just basically it's going to repeat this byte and XOR it with the key stream. And if we didn't give it that, it would just pick whichever one was the longest, which should be the key stream anyway. Maybe we'd have actually, so the first time through when there is no key stream, it would XOR to the longest one, and since there is no key stream, this would throw an error, so we need to explicitly state the key stream. So the first time through, we're XORing 0 times because we don't actually have any key stream yet. I knew not to trust myself. And then what we'll do is we'll send this IV along with the actual block we're trying to recover. That is what we're going to send to the oracle. So if oracle get encrypt is valid padding, the IV plus the block, if that is valid padding, then we know we just recovered a byte of key stream. So, and we're working backwards, so we need to put this, the byte we just discovered, at the front. And then what we discovered is now we have the byte, where is it? We have the byte that made it work, and we need to XOR that with the value we're trying to get, because remember, so we have a key stream, the IV, and the plain text. And to get the key stream, which is what we want, we're XORing the plain text and the IV. And the IV byte in that position was B, and the plain text byte in that position is I, because that's what the valid padding decrypted to. And then we're adding that to the front of key stream since we're working backwards. So we're going to get the 16th byte first, then the 15th, then the 14th. So that's why we're doing it this way. And then since we found that byte, we don't need to check any of the other ones, so we can break. And then that'll break us out of this loop, and it'll increment I to the next one and repeat this process over. So it'll keep doing that until we've 1 to 16 will be the final one. So the last time through, it'll be 16 minus 16 is 0. And when you put the 0 there, it basically will be none of the IV. Ooh, we're changing the IV every time, though. Actually, that won't matter because we're effectively rewriting the whole thing. And we're never changing in front of all this stuff, so that's fine. So once we've done that, then that means we have the full block. Once we get to this point, right, we're through here, that means we've completely recovered all 16 bytes of key stream. So we can now figure out what that block of plain text is, and that will be the XOR of the key stream and the previous block, right? Because as we said, we'll use the real previous block now. Each time we figure out the key stream, we need to XOR it with the real previous block. So we XOR the key stream with the previous block, which we set to be the IV the first time through. Oops, previous block. But now we need to make sure and set previous block to the current block so that the next time through, we get, so that when we're working on this one, we need to set the previous block to what the one we just did, because that's what's going to get XORed. And now we need to return that. And that is bytes. That should be it. Now, because of the joys of the fact I'm just doing this without an ID, we'll see how many random dumb errors I get. So challenge 17. Yeah, I'm printing it. All right, fingers crossed. All right. Padding Oracle has no attribute messages. Line 26. Oh, I thought I fixed that. Messages. And the other thing is I'm terrible at spelling and typing. So key steam is not defined. So that's line 54. Yeah, there we go. And I spelled it wrong here too. Key steam, key steam. Did I screw that one up over here? No, got that one right. Oh, all right, we worked it. It's only 2 typos, not bad. Well, this here is the padding. Oh, I think I know why. I was gonna say this looks really weird, and it was kind of like made me panic for a minute. But then I remember like these all start out the same. So like, what I'm guessing is, I don't know why it's so many zeros, but I'm guessing this is the 5th message. So 1, 2, 3, 4, 5. Let's see what this actually. Actually, let me do this way. Since I don't have as much room to type, because I tried to make everything bigger. Oh, 0, 1, 2, 3, 4. So, all right. First one must be 0, 0. But we can see they did do it that way, so I'm pretty sure we got this right. I mean, obviously we did. Yeah, go crazy when I add a symbol. And I didn't unpad these. So what we could actually do is we'll unpad these. Plain text. Black size. So yeah, cool. But yeah, I really like that attack. It just, I mean, imagine being a developer, right? And like before you kind of like, I think this is well known enough now, people probably know about it, but like, you're like, oh, our key's secure. Like we're not, you know, we're not giving them back. We're not giving them back the decryption. We're not like doing anything. We've just, we're processing a, Java web token that we've got some encrypted stuff in or whatever. And all of a sudden, your encryption is broken. Like you would never even think about the fact that like just someone giving you something and then being able to figure out whether or not a message they gave you had valid padding or not, they can completely recover everything. I don't know. I really like that. So, yeah. Now on to, oops, I went too far back. We're going to implement CTR next. Okay, so if everything, poof, suddenly looks a little bit different, it's because the power went out. Thankfully, I had stopped the recording after challenge 17 to go to the bathroom, so I only lost like 10 to 15 minutes. But that means like since my VM just like shut down, so I lost like the positioning of everything. So like the windows are a little different size. I think the fonts might be different. I was thinking about trying to like recreate everything to make it look exactly the same and then just like splice them together so it wouldn't be noticeable. But I realized like, I don't know, that's kind of silly to put that amount of effort into something like this. And especially since a big part of the reason I'm making these videos and in the way that I'm making them is to just like get over that kind of stuff and just get some practice at putting out videos and not worrying so much about like all the mistakes that no one really cares about but that bother me. So we're just gonna jump right back into challenge 18 and get going. So we're going to be implementing CTR in this challenge, and basically the way it's going to work is what CTR does is it changes AES from being like a block cipher to a stream cipher. So like block cipher, everything like the message, that's why we have padding, like the message and the plain text or the crypto text, everything is like gets fed in blocks at a time. And in a stream cipher, you're just getting bytes and you're XORing and as you need bytes. Well, so that's kind of what is happening. What CTR mode is designed to do is basically what we're going to do is we're going to have an 8-byte nonce and an 8-byte counter, and we're going to encrypt them, and we're going to run that through the AES, and the key stream is what we're going to use to XOR with the plain text or the ciphertext. So like to encrypt something, we're going to XOR the key stream with the plain text, and then to decrypt, right, since that's how XOR works, if we have a key stream, a plain text, and a ciphertext, we can XOR any two to get the third. So if we XOR the key stream and the plain text to get the ciphertext, to decrypt, we're going to XOR the key stream and the ciphertext to get the plain text. And some of the advantages of this are then you have kind of a stream cipher. You don't have to know exactly what length of the message is you want to encrypt. It doesn't have to be divisible by blocks. You can just keep incrementing the counter and you'll get a brand new set of key stream bytes that then you can then use. You can also encrypt and decrypt in parallel, since the only thing that's going to change, because the nonce always stays the same, so the counter is what changes. So you could decrypt and encrypt in parallel a whole bunch at once, because nothing in here is relying on the previous block or needs to depend on what the message is or the ciphertext or any of that is. You already know ahead of time what these will all be, what key stream is going to come out, so you can go ahead and do that. The gets kind of confusing. I don't really know that well, like kind of the nuances between like what's the difference between a nonce and an IV, because all IVs are nonces, but not all nonces are IVs, I think how it works. Anyway, a nonce basically stands for number used once, And an IV is, you're only supposed to use it once, but it's supposed to be generated in an unpredictable way, where a nonce doesn't have to be. Like you could use like some kind of counter for a nonce or stuff like that. I think that's actually how I think the Wi-Fi encryption is done, if I remember right, that's how it's part of how it's broken, because it used packets as the counter. I can't remember. Anyway, but you have to make sure, right, number used once, because if you reuse the nonce with the same key, and if your counters are always starting at 0 or whatever, like you can only use it. Obviously, if you reused it, then someone would be able to get your key stream, or that's not secure. So anyway, let's just go ahead, and what they've done is they've given us a base 64 encrypted ciphertext, and they've told us the key used and what the nonce is. And a difference here in this, the way they're doing it here, than like PyCryptodome, is this is little endian encoded. So little endian, like here, let's look at, this is the counter. These 8 bytes here, little endian. So in little endian, the least significant bit is on the left, and in big endian, the least significant bit is on the right. So big endian is what you're used to seeing. Like if you were going to write out a number in binary, kind of like how we read numbers from left to right, that number on the right is the smallest, the least significant part. Like if you have, decimal 197, like the 7 means there's just 7, but the 90 means there's like 90 of them, right? So like 7 is least significant. So basically little endian is backwards. There's probably a mnemonic to remember it, but I don't really know one. I just would always have to look it up until finally I remember, oh yeah, little endian's backwards. The other thing is, with the CTR, we're gonna make it so that once you encrypt with that setup, you can't decrypt, right? Because you're gonna have a counter that's always incrementing, so you have to recreate it with the same initial conditions if you want to decrypt. So let's. So, actually, I'm kind of confused now. We're just going to be changing our the AES implementation we've already built in the previous challenges to add a CTR mode. And this value is going to be different than what the one in the PyCryptodome, because I'm pretty sure this is the last AES. Like we're not going to implement any of the other modes. And I actually kind of talked about this on what got erased, is I'm going to kind of change some things up. So like ideally a better way this would have been handled is if we were going to do all the modes, instead of creating just one sort of AES that we try and handle everything in, it would have been like each mode we create a different, like it just has a different cipher, like a different entire class that's built specifically just for that mode. And then we would, depending on how we wanted to set it up, this new would get it to that. But since that's not what we've done, we're going to kind of have to shoehorn this in a little bit. And it'll be okay, given that we're just doing these 3, but this would be something that if we were going to like go on and make more of, we'd be either better off kind of like redoing it to make it better like now, or have planned, well, the best way would have been to plan from the beginning. But one of the things that we're going to kind of change is that the only mode we need an IV in is CBC. And then now we also need to add room for a nonce and an initial value. And depending on, they don't need to have an initial value, and if they don't supply a nonce, it's random. So it gets kind of like, I don't know, the way to handle all this gets kind of cumbersome doing it like if we were just going to add nonce and then we'd have to put IV afterwards, which means now, because right, we give it a default, which means now everything else we've written isn't going to work. We'd have to like go back and like change to make it work. So what we're going to do is actually, we're going to pass in, from this point on, we're going to pass in args and quargs, which I think I went over a little bit in the XOR video, but I'll kind of ramble about that again in this one. And then we're going to not deal with the IV and the new, and simply new is just going to return the new AES or the AES class with our args and our quargs. And then we'll fix kind of everything, how we handle it inside the actual AES itself. So what we're going to do now is, let's see, we need to change a couple things. First, we need to add a mode, right? We have another mode now. And then we are going to change this where it was always handling an IV, where now we only need the IV if our mode is CBC. And then what we're going to do, since we have it where they don't have to give us an IV, like the way we've previously built this to be compatible with all, everything else that's been written so far, is to make it so that if there is no IV passed in, then I need to change these too. If there is no IV passed in, then what happens is we create a random one, and if there is, we use it. So if there is one passed in, it'll now be in quargs, because the way it'll work now is if anyone calls it, so we're going to set up our nonce. So like, let's say they were going to create an AES. So in their whatever program, I'm just using this example, so ignore that I'm writing it here. They'd call AES new, and they'd give some key. They'd give the mode, and then if they want to specify a nonce, they have to say nonce equals, and then whatever the nonce is. And if they want an initial value, they'll have to specify initial value equals whatever that is. These are in the quargs, right? Because these are key values. Where the way we had previously had it, if they were using an IV, they just passed it in. It wasn't an IV equals whatever they made. So this will get passed in under args. So what we're going to do then is, where was I? Okay, yeah, so if it's CBC mode, then we want to check and see if they passed in an argument. And if they didn't, we want it to be a random 16 bytes. So the way we're going to do that is we're going to check args and args0 or urandom 16. So what this is going to do basically, well, logically, like we could think about it like this, right? We want our IV to be equals the first arg in arguments, and if there isn't one, then we want it to be urandom. But we can't just perform this check, because if there are no arguments passed in, like if they didn't give us one, this will throw an error for index out of bound or whatever. So first we need to check if there are arguments, if there are args. So IV equals args and arg0. So whenever you have an and statement like that and an or, so the way most programming language works is called, what's it called? Short circuit evaluation, I think. Once it's determined whether it can know the final answer or not, it doesn't keep looking. So like right here, if you have an and an or, like if this first one, so think about just an and, right? If you had args, actually let's do it. So like if I have like if 0, I don't even need to do this. Let's do 0 and 5. For this to evaluate to true, both in an AND statement, they both have to be true. So it'll look at the first one. Here, let's even make it more explicit. Let's say false, false, and true. It sees the first one is false. It never even bothers to look here because it knows no matter what, this statement is going to be false because that's how an AND statement works. So you also have, let's say you have true, or we can put anything here. Like, I don't think this will throw an error, even though this isn't actually a thing. Maybe it will, maybe it won't, but hopefully it doesn't, because that'll make this point hit home even better. If you have a true or, it doesn't care at all what is in this spot. It already knows it's going to be true. Yeah, okay, so it didn't even look at that. But if I had it the other way around, I think now I'll get an error because it actually evaluates that, and that's not a thing. Ah, sweet. So once it sees, it knows the answer, it short circuits, never even looks at that. So we're going to use that to our advantage here in that we're going to check args. So if args doesn't exist, this is a false. Like if args is none, there's nothing here. This is false, so it doesn't even look at arg0. And then it, because it's an OR, now it has to check this, and it'll create that. It'll set that equal to that. But if this is the case, the way AND works is you get whatever the last evaluated one is. So like if we have 5 and 2, it's going to return 2. Whatever is in that spot is what will get set when you use it as an assignment. So here we're looking, we're going to say IV equals args and arg0. So if there is no args, it just short circuits past that and then sets it to urandom 16. If there is an arg0, then it short circuits, never does any of that because it already knows this true or something is always true. So it takes this value here and sets it to IV. So I don't know. I probably went on way too long about that, but hopefully, why did that not? Oh, hopefully that makes sense. I thought it was supposed to indent, but we're not doing ifs. And then we can check. Now we can check for our now we can check to make sure that the IV is bytes. So, and that it's 16, right? Because now we still need to have this check to make sure that what they passed in, if they did pass one in, like if they didn't, we know this, it'll pass, right? Because we created 16 random bytes. But if they didn't, it got set to arg0. So we still need to check that, see if IV is bytes, and then it's 16. And if it's not, we're going to throw a value error. And then what we'll do here is now we'll handle all our CTR mode stuff, which is going to be dealing with our quargs, whether or not they've set a nonce or have an initial value. And what we want is I don't think they say here, maybe I was reading it in the PyCrypto Dome. We want it to be able to like have it be, they can pass in an integer for the counter, or they could pass in the bytes. So like if they wanted to pass in, like if you're going to recreate this, we want them to be able to pass in either. And we also want it so if they don't give us an initial value, we just set the counter, to 0. So we're going to handle all that if our mode is equal to CTR. So we have our if it's CBC, and then we'll have all our if it's CTR. So we want, if they don't give us a nonce, we want to make a random one. But since the way we're going to check that, and I think this, I talked about this in the XOR, but we'll use quargs pop nonce, and the default will be urandom 8. So what this is doing is it's going to get the quargs, and it's going to pop off nonce equals and make nonce whatever that value is. Unless nonce isn't one of the things they put in the quargs, then it's going to set it to urandom. So it'll either be their value or the urandom value. And then we want to do the same thing for initial value. And I'm actually going to explicitly call it initial value so we don't kind of confuse it with the IV. And the initial value is basically what we want the counter to start at. And so we'll do the same thing. We're going to pop off initial value. And if they don't give us one, we want to set the default to 0. And then we're going to do a check. So we've popped off both. So pop takes it out of the thing. So now we can do if quarks, and that means if there's still anything else in there, that means they passed in some random gibberish, like, you know, foo equals banana. So like they gave us something that we don't know what it is because we're not using any of that. So we'll actually raise a type error. We'll say invalid parameter parameters for CTR mode, and then we'll show them what invalid parameters they dared to pass in. Then what we want to do, let me make sure that's right. Yeah, if quarks looks good. Then we want to check and make sure our nonce is actually bytes and that it's 8 bits long, to make sure they didn't pass in something not in bytes or not in 8 bits. So we'll do kind of like how we did with everything else. If nonce is bytes and length of nonce is 8, then we'll set nonce to our class variable to nonce. Otherwise, they did something bad, and we are going to throw an error. So we'll say that would be a value error. Value error. Let's just say nonce has to be 8 bytes. And then now we want to handle our initial value. So we want to be able to accept integers and bytes. So let's check if initial value is an integer, which will happen either if they gave us an integer or they didn't and we set it, because we set it initially to an integer, we set it to 0. Then what we're going to do is, we will then set initial value. We'll convert that to bytes. And the way you do that is 2 bytes. How many bytes you want it to be, and what format. Little Endian, big Endian. And we want little because they specified in the challenge that we're using little Endian. Now we can check if instance initial value is bytes, right? Because if they gave us an int or we set it ourselves, we've converted it to bytes. Or if they passed in bytes, it's bytes. So they could have passed it in, so we still need to check now to make sure it's bytes and it is 8 long. And if it is, then we'll set initial value, the class variable, to the initial value. And if it's not, then we'll throw an error. Let me make sure I did it, because if they give us an int or we set it, whatever int they gave us, we're converting to bytes. So we don't need to do any kind of error there. So we end up with bytes no matter what, and then we can throw our error here. Now, one way it could go wrong that I guess you could check for is, right, say they gave us an initial value, a number that was bigger than 8 bytes. When we convert this, so like let's say we have a equals, smash the wrong keys. That number is bigger than 8 bytes. And if we convert that to bytes, I think it will just convert. It'll take 8 bytes of it. We'll see, maybe it'll give us an error. I don't actually know. Okay, cool. So it'll throw an error for us, so we don't have to worry. I wasn't going to make one anyway, but I was just saying that is something to think about. If you did need to check for that for some reason. So if they we're going to raise a value error. Initial value must be 8 bytes. And then what we're going to do, if we pass through all that and we got everything right, and this, there's probably a better way to do this, and this is one of the things that I get frustrated, I get frustrated about and like end up stressing and spending way too much time on because this doesn't feel like the most efficient or elegant. I'm sure there's a much better way to do this. Okay, we're going to set the counter to an integer because we're going to need to increment the counter, and it's just easier to increment if it's an integer. I believe it's int from bytes, pretty sure. And we're taking our initial value and we're converting it little endian. So what we kind of ended up doing in some cases is going from an integer to bytes back to an integer, and then when we actually encrypt and decrypt, we're using the counter that is now an int. We're going to have to convert it back to bytes. But it just kind of makes sense for me to flow this way. And instead of spending forever rewriting and looking up how should you handle this and like stressing about it, it's like something that I end up doing where I don't get stuff done. Like, you know, I have a lot of projects where like I never finished it because it just feels so ugly and inelegant to me, when it'd be much better off to just have working code. Right? Like if you have to write, I don't know, 1 million lines of code to really kind of finally get good at writing code and start being able to write like, you know, elegant, great code, and I'm stuck at line 104,000 because I spend forever on the lines, you know, 104,232. I'm just doing myself a disservice by not being too stringent with like, this feels gross. And who knows, maybe this is just fine anyway. We also want to set, like I said, once you encrypt, you can't decrypt. Once you decrypt, you can't encrypt. You have to make a new instance with the same starting condition. So we'll have two variables called can encrypt and can decrypt. And we'll set those to true initially because you can do anything you want. And then, so I think that should be good with that. Args, quargs, I guess we'll find out when we go to run it, debugging. So we handle the IV, we handle what we're doing at CTR, so that will set everything up right, and now they can call encrypt and decrypt. And again, we'll handle, if you weren't around or don't know what we did for this function, right? We set it all up based around these two things. The only time we're actually doing anything with AES is in this encrypt block, where we're just encrypting a single block in ECB mode, and then we built up everything else around that. So we'll be doing the same thing here, and these were our callable functions, right? So in whatever program you would just call encrypt, just like you would in like the PyCryptodome, and then our logic here will take care of everything, hand it off to where it's supposed to go, and give you back what you want. So we need to change some stuff up in here because there's a couple key differences. Everything we've been doing now so far is blocks, like it has to be blocks. Like we have this error here, plain text must be a multiple of the block size. We don't want that anymore. We still want that, but not in the case of CTR because it's a stream. We're using it as like a stream cipher. It doesn't, messages don't have to be multiples of the block. So we want to change this a little bit to say if self mode is not mode CTR and length plain text. So now this this only gets evaluated if it's not CTR mode. If it is CTR mode, then carries on like normal. And we want to remember to do the same thing here. So if mode does not and then we'll still go ahead and carve it up into blocks. And in the case of CTR, try and make this a little bigger when we're not using that. In the case of CTR, it won't matter that the last block is just a little bit smaller. So this will all stay the same, and now we need to add a condition for if we are in CTR mode. And I probably shouldn't use 1, 2, 3, right? I should make it more explicit. So when you're reading the code, like you don't have to remember like, oh wait, what's mode 1, what's mode 2, what's mode 3. So that actually would be a better way to do it. I'm gonna go ahead and just leave it as 1, 2, 3 because I don't want to switch now. And I don't know, I'm not gonna go back and change everything because I don't know, then if someone else for some reason is watching video 2 and they look at the code on the GitHub, I don't know, I want it to be as close as possible. But again, that doesn't really matter. So we want to check if we can decrypt, right? Because if we can't decrypt, we don't want to pass this on. So if we can decrypt, we want to now make sure we set can decrypt to be false. And we want to, we'll pass it off like the other ones. We'll pass it off to a function called CTR encrypt, and we'll hand it the blocks. And then if we can't decrypt, we throw an error. Encrypt cannot be called after decrypt. And I guess really, I'm not going to change it because I'm stressing about dumb things that probably don't matter that much for our purposes. We call this here, like what happens, right, if they go to encrypt and then later down the chain in this, it throws some error so they never actually decrypted or encrypted. We might not want to set this to false yet. Like we want to make sure it actually something has been actually encrypted before we change that. That might be a consideration. I don't know. And then we want to do the same thing over here. Self. We need to check the same if can decrypt. Then we want to set can encrypt to false. And then we want to return CTR decrypt with blocks. And if that was false, then we throw type error, same thing, decrypt cannot be called after encrypt. So we handled our case and decrypt, we handled our case and encrypt. We should now just have to write these two functions, CTR encrypt and CTR decrypt. Let's go ahead and put it below CBC. So we'll do CTR encrypt and just use what's already provided for myself. We're taking blocks that are bytes and will be returned. Oh, actually, hold on. Our blocks are is a list of bytes. I didn't notice that I had it like that here too. So if anyone was using a linter on the other stuff, I assume. Oh, I did it wrong on all of them. I mean, I didn't even have a list. I have it as bytes. Whoops. And then these obviously are just bytes because that was our primitive we built it up around. Where was I? Oh yeah, and then I'm going to return bytes. And then we'll have a CTR. Now we probably could actually, so since encryption and decryption, I should talk about that a little bit, are the exact same thing, we could actually combine this just into one function. And I don't know, call it like, because we're basically going to like duplicate the exact same code in both of these. So we could probably combine it into just one function, but I'll go ahead and leave it as two, even with the duplicated code, just for, I don't know, explicit state. So, okay, we're going to have a result, right? Actually, we'll go ahead and use the specific term since we are making separate. So we're going to encrypt something. So we're going to have a ciphertext. And then we're going to iterate over our blocks for block in blocks. And then we need to produce a key stream. And all the key stream is the encryption of the single block of what our nonce is, plus our counter, which we remember is an integer. So we need to, like I said, we're going to convert back to bytes. Self counter is an int. We're going to convert it to bytes. We want 8 bytes, and we have to remember it is little endian. So that gives us the key stream. And then we want to increment the counter. And then the result of that block, we will append to our ciphertext. So what we're doing is we're going to XOR the key stream. Oops, the key stream and the block. And what we need to remember is that our block might not always, like the last block might not be the same size as the key stream, because the key stream is going to give us 16 bytes and the last block might only be 1 byte. So if we didn't do anything here now, the way our XOR function works, it would repeat block to make it the same. It'll make both these the same size, whichever is the biggest size. So it'll just like repeated key the smaller one to match the bigger one. And so we want to use the smaller one. So we want it to be the size of the smallest one. Because if our block is, say, only 4 bytes, we only want to use 4 bytes of the key stream. And then we can return our ciphertext. And we're basically probably going to screw myself here because, like I said, I try not to copy and paste anymore because long term, it's probably cost me more time in finding bugs than it saves me to type everything out. But since it is basically exactly the same, except our variable names, I'm going to go ahead and gamble. Plain text equals key stream block length min. That should be right. So see, what I basically mean is like we could change the name of that to like, I don't know, result or output or data or whatever, and combine these into one function because it's basically the exact same thing. That's one of the kind of benefits of a stream cipher is that encryption and decryption are like the exact same process. Basically, there's not a separate way you have to do it. I think that should be good. Let's go ahead and we actually have our challenge 18. Let's see what it was they wanted us. We want to decrypt that. Oops. So in our challenge 18, we're going to have to import AES. We don't need padding. That's all we need to import. And then we'll have, oh, we will need base 64. So all right, so we have our ciphertext. Oops, wrong one. Control V. And then we want to decode that. I guess I should just, here, let's do it in one line. B64 decode. What they say our nonce was going to be the byte value 0 8 times. We don't need to set the initial value because it should start it at 0. We'll need our cipher. So, oh yeah, our key was yellow submarine. All caps. So we need the key. CTR mode. And nonce equals nonce. And then we want to decrypt our ciphertext. We'll make that the plain text. And then we'll just print that out and see if it works. So I'm sure there'll be a bunch of bugs that I typoed and all kinds of fun stuff like that. So let's see what we get. Should I save that? B64 decode. Deosode. So all right, over under on 5. we're gonna end up with 4. So we've got 1. Quarks is not defined, line 31 in init. What do you mean quarks is not defined? If quarks.pop. Oh, cargs. There's 2. Instance is not defined. Oh, line 35. Did I spell instance wrong? Oh, it is instance. Oops. So I should probably have all that. Or else did I call is instance? Oh yeah, I didn't change any of those. Okay, so what was that, 3? We're at 3 now? 4. Decrypt. That would have been another one. Oh, I nailed it. That was 4, right? I went under. Didn't I say they did before? I don't know. So yeah, so we see it worked out. Let's go ahead and, well, it'd be exactly the same, but I'll go ahead and let's encrypt it. I mean, the process is exactly the same, but let's make sure I somehow didn't typo in the actual separate encryption function I wrote. Let's print, oh, we have to make a new cipher. Let's check that too. Like, so watch, if we tried to now decrypt the plain text, or no, we want to encrypt the plain text, sorry. It should throw an error. No. Oh. No, yeah, it should throw an error. Well, let me think here. So we decrypted. It should no longer allow us to encrypt it. Oh, maybe I didn't save it. No, so somewhere we do have an error with our can encrypt, can decrypt. We set it both to true, and our encrypt. Oh, here's our problem. If so, we're encrypting. We have to check to see if we can encrypt. If we can, then we're going to encrypt stuff, and we'll set decrypt to false, and then in decrypt. Oh, wait, why are these not highlighted? Oh, they aren't here either. I'm looking at that. So can decrypt, we set can encrypt to false. Yeah, there we go. So again, like if I was making this for like not just this specific challenge, you'd do a bunch of tests and you'd make sure to test everything. Let's go ahead and check that we can, well, we need to create a new one. Let's just call it cipher. Same key, we're doing CTR, our nonce is the same, and let's encrypt that plain text. And we'll make sure that it comes out to be the same as what the original ciphertext was. So print CCT. Did I not? Oh, yeah. Yeah, okay. So there we go. Oops. So that is challenge 18 done. Right, that's all we needed to do for it. Decrypt that. All right, so on to 19. Okay, so 19 and 20 are pretty much the same. I actually think I'm gonna just combine them. Yeah, so this is giving us a bunch of different base 64 encoded ciphertext that were all, right, they made the flaw of not changing the nonce. So if we go back to the thing, they're basically encrypting all the different things with the same nonce encounter for each message. So this one does it nonce 0. Does it say what the nonce? Actually, yeah, nonce 0, and then counter. Like we don't know the key, right? But they're using the same. So it encrypts that, then it starts over. Nonce 0, 0 is the counter. So basically, they're all of these are encrypted by the same key string. And so there's 40 of them. Yeah, and they want us to do this manually. So kind of like, I'm not going to do it for a couple reasons. One, basically you do like exactly what we talked about in one of the earlier challenges where you use letter frequencies and try to figure it out. Like, you know, we get each first byte was all encrypted by the same first byte of the key stream. Each second byte was all encrypted by the same second byte. So it's the exact same thing as like repeated key XOR, which we already broke, and we already like wrote how to broke, like we wrote the program to break it. So really this is 19, they want us to do it manually, which not very beneficial for a video. And I don't know, like you can go over, if you want to do that, like go over one of the earlier one, like where, I don't remember how in-depth I got, but it talked about like letter frequencies and all that stuff. So 20 is the one where they give us this big file and they want us to do it statistically. Yeah, so they even say it's the same as repeated key XOR, but with fixed nonce. They are effectively the same thing, which is true if you think about it, right? Because it's basically just one big long key of the same key string. So not all the messages appear to be the same size. We do need to, so we'll copy this and we'll put this in our challenge 20. So there's 60 of them. Yeah, they're not all the same size, but again, it'd be the same as if like we repeated key XOR ones that weren't the same size. Like we can take whatever the shortest one is, and we'll have enough statistical data from all of those to break it. So that's actually what we're gonna do. I'll do it like this because we're going to combine them. So 19 and 20. And right, like, oh, where am I going? Hopefully that kind of like makes sense why we're doing it this way, in that it basically is the same as repeated key XOR. So we're not going to do anything at all differently than what we did. What challenge was it? Because we'll actually just reuse that code. Was it single byte? Yeah, so we scored English text, and yeah, that's how we got the key. So it was challenge 3. I don't really remember what we labeled. Yeah, so here was our frequency stuff. Remember, we got the vectors, did it a little bit differently than kind of like the way I think most people approach it. And we basically, the function we're going to want is this get single byte XOR. I'll leave that open. Did I open 1920? Okay. So, let's do our if. We'll just sort of write this out and then we can fill everything in. So we are going to want hold on. Oops. Set 3 challenge. Base 64. Okay, so we have to encrypt them. Okay. I guess that makes sense. Well, not really. I don't know. Gives us a chance to practice CTR. Just typing it in, I guess, because now it's abstracted away, so it doesn't really matter. Okay, so we'll have our plain texts. We'll do our standard parse input with the name of the file. What would I call it? Challenge 20. And then we will encrypt all those. So we'll have our ciphertext, and we will, yeah, because we're going to have to encrypt each one with the sync. Yes, I'll do it in a function. I was thinking if I could do some kind of list of comprehension, but that's not really going to. So we'll call it CTR encrypt plain texts, and we'll give it the plain text. And then we want to use the shortest one, because that's what we'll get the, like for the key length is what I mean. So like whatever the shortest encrypted ciphertext is, they're all longer than that. So that's kind of where we'll break it off, right? Because like after that, we could probably get a few more depending on how long the other ones are. But eventually, like there's going to be one that's longer than all the rest. And you know, there's no way to break that at that point because we don't have anything to compare frequencies to. So we will just have our key length be the minimum of the length of the cipher minimum. So if we do like, I think I can do it without making it a list for CT and CTs. So we'll have this generator and enumerated thing of the length of all the ciphertexts of each ciphertext in the ciphertext, and we want the smallest one out of that. And then we're going to recover the key. And then we will loop. We need to break the XOR for each. Yeah, so we'll do, I'll just write it out. And then if there's a better way to make it shorter and more efficient, I'll do that. So just like in the earlier challenge, the first byte in every ciphertext was encrypted, was XORed with the same keystream byte. So we need to take the first byte from all the ciphertexts and combine them into one, because that's what we're going to run through the function. So that it's just like then it would be like it was encrypted with the single key XOR. So we will say ciphertext equals, we will join the, yeah, because one, okay, I'm just trying to think of, we do need to make it, I'll write it out long way because I'm confusing myself. Basically, we want the, for CT and CTs. So we want to get the first, or whatever byte we're on, right? Like when I is 0, we want it the 0th position byte in all of them. When it's 1, so we want it like this. And when you slice a byte string, just get a position of it, it returns an integer. So we need to convert that to bytes. But it's already an array, so we can just pass that into the bytes function. So now this is bytes. So now we have a byte array, and we want to join all that together because our function that we're going to pass it into to crack takes a byte string. So then the key will be get single byte XOR the ciphertext. So now we know what the key is. And then we can check and make sure what we got right. We know what the actual plaintexts are because those are just, yeah, those are just base 64 encoded. So we know what we're supposed to get. And we know what the key stream for everything is because they told us, oh, I guess we'll just use whatever key we want. So anyway, we know what the key string is, our key stream is. So then that's how we can check to make sure we got it right, because then we can just compare it. I don't know why it's so confusing to me right now. Yeah, so we have the key, and then we can decrypt all of them. Or we don't even, sorry, we don't even need to, what am I thinking? We don't even need to decrypt, we're just XORing. So then we can XOR all the ciphertexts and see if we get the same plaintext. So let's do for ICT and enumerate CT. So enumerate, I don't know if I've gone over this one before. Basically, since this is a list, like normally it'd be like for ciphertext in list, you know, it'll assign ciphertext to each one. If you enumerate that, you also get the index. And we want the index because we are going to do, we want to compare it to that position in the plaintext. So we could do like, I wonder if we should just print them all out. let's do it like this. So we'll print everything, and we'll say the actual plain text was supposed to be that. And then what we recovered, I'm going to make these line up. So I've got 6 letters. Let's go recovered. What we recovered is going to be, we'll just XOR these. So we're going to XOR the key and the ciphertext, and the key will be the smallest. Because remember, like, we went to the shortest ciphertext. So we'll do it like that. Key length minimum. And then let's put another space. And that should be, so now we just need to import all our stuff. We have 2 other functions we wrote. So we need our parse input function that will take a file name. And oops, and it's going to return a list of encrypt plain texts. Make it return a list of bytes so that when we pass it in to our, we'll stick with my bytes in, bytes out for encryption. And then we'll have a ctr encrypt plain text. Our plain text will be a list of, a list of bytes, and we are going to return a list of bytes. And then let's see, we're going to need our AES because we're going to have to encrypt everything. We're going to need our utils. What? Oh. Wow. From. Sheesh. I already wrote import. Import. XOR. No. We're going to need base 64. Base 64 decode. Oh, and then from challenge 3, we're going to import get single byte XOR. So to parse the input file, we'll do our with open file name read as f. Let's say plain text equals base 64 b64 decode. What's the format of this? Oh, did I already close it? Okay, so let's just do line, strip out the new line at the end, or line in F, and then we can return that. And then this function will guess we just use whatever key we want. Instead of making what they tell us to do in the first. Nonce value to generate random AES key. Okay. Do our standard urandom, which means I need to import urandom, and then our nonce, they said to make it 0. And And then our ciphertexts. I won't use list comprehension because we're going to have to create a new cipher every single time, or a new CTR object thingy. So we'll do it like this for plain text and plain texts cipher. We'll say yes, new. We give it key. We give it yes mode CTR. And we tell it what our nonce is. And then we are going to append the encryption of that plain text. That way it creates a new one every time, so it's starting over with the same key and the initial value of the counter, so that they're all made sure to get encrypted with the same key string. Key stream. That should be it, I think. Let's see. So we're parsing our input. We are encrypting all of those. We then need to get the key length. Then we will get the key by getting that position in each of the things, because those were all XORed by the same byte. So then we're going to break that with our statistical tests. That'll give us the key, and then we're enumerating. All right, I know I just have like low belief this is going to work on the first go. No such file or directory. Resources. Challenge 20. Where did I actually save it? Did I not save it? No, I saved it because I even had to reopen it. Well, where's Sublime Text? Tell me. Oh, it's hidden under the frame for the recorder. Resources challenge 20. Oh, duh. So basically I was telling it to look, if you're not familiar, so this is look in the root directory, resources, challenge 20 text. This is in the directory you're in now, go to the resources directory, challenge 20. Expected a bytes like object int found. So that is right here. Okay, CTI. Oh, no, that's right. That should be an array. Like, I feel like if we passed in an array of bytes into that, oh, we don't need to join it. CTI for CT and CTs. So maybe we just go like that. Oh, sweet. All right, let me make this bigger. Okay. So we got it all. I mean, we did it right, but if you look here, we got the first one wrong on every single one, which makes perfect sense if you think about it, because if you look here, the actual is what the thing was. If you look here, they're all capitalized, and in our where was it? if you look here, all our letter frequencies were lower cases. So I don't think we ever convert anything when we break. And not only that, too, this is actually thinking of this because I've been playing Wordle a lot, and I was going to write a program to like figure out the best solve, like best first word, and be able to always solve it. Anyway, if you think about it, the way this is distributed, this is the distribution of the most common letters in written works of English language. Like I'm like, look here, we have a space is 18% of the time. Well, this byte is not that same distribution. It's the first, we know for a fact, it's the first letter of a word, and it looks like it's often the first, it's the first letter of a sentence, so it's never going to have a space. It's also the first letter of a word, and that has a different letter frequency. Actually, let's look it up. First, most popular first letter of English words in growing frequency. Because I want the Wikipedia page. Yeah, because I think they actually have a chart. I remember this from doing these one of these times. So relative frequency in the English language, text versus dictionary. I think there's one for, yeah, first letters of a word in the English language. So if we look here, like we know English, or E is the most popular letter in the English language, but it's only 2% of the time it's the first letter of a word. Like if you look, these are going to be completely different than what our what our frequencies are. Not only is there no space, but see, we have E at 10%. So basically, what I'm trying to say is the reason it worked so well for repeated byte XOR was because that, or even the short, like the repeated key, like I think they use the key ICE over and over and over again, because you're getting essentially kind of a random distribution of letters. Like you never know that it's not going to line up with words. I'm probably not making sense, but it's basically them as a random distribution, where what we're doing here, because we're encrypting, or we're doing it with like these strings, it doesn't quite work out the same. Like even our second letter, right? Like how often is the second going to be, like that's a testament to how good our actual algorithm with the dot products and letter frequencies works, because we still got, everything right but the very first one. But if you think about it, even the second letter is going to be a different frequency than what we have, right? Because there's no spaces. I'm sure you're going to get a lot of like diagrams and trigrams, like, CH is much more popular to start a word than, random. So things like, the, SH, TH, CH. So H probably has a much higher than normal letter frequency for the second letter than you would expect what the frequency of H is for any letter, right? So, but we still managed to get everything right but the first one. So one way to fix, like, right, obviously from context, we could figure out, we'd only need one of these to know, like, if we had all of that, we could look at it and figure out, oh yeah, it's probably cuz. So we'd be able to figure that byte out. Otherwise, you'd want to write it in, you'd have a separate, which is kind of one of the reasons I'm lost. Did it this way, where we had English frequencies, right? You could have another dictionary for English frequencies first letter, English frequencies first two letters. You could do a bunch of different things and then have it use the different dictionaries. Anyway, I guess I shouldn't have gone on about it that long, but I don't know, I thought that was actually pretty interesting that we got it wrong, but it makes complete sense why we got it wrong. Let's also, just for fun, let's go ahead and let's do the same thing, but let's break challenge 19 now, because we can just go right, we can just put those in that text. Doesn't look right. Chal 19 text. And then in our you know what? Let's go ahead and do this. Let's make challenge 1920 just be challenge 20. And then let's make a challenge 19 where we'll copy challenge 20. But the only thing we're going to change is, so now we'll do the same thing, but with just those, these. It'll be much shorter, right? Because the shortest one is going to be shorter, but we'll see. And again, we should probably get the first one wrong, depending what these are. Did I save all this stuff? I'm not typing it right now. Oops. Oh, okay. Well, I don't get that now. So now we get the first one right, but we get the lowercase instead of the uppercase, which shouldn't be possible because we're not looking for uppercase. Oh, that is weird. And it's still the first letter of a word, right? So I don't get why we got it. We still got it wrong, but now we get the lower. So maybe it's because they're all shift, right? So the lowercase of a uppercase, I forget which is lower. I think the earlier ones are the uppercase, and then it's always 32 numbers later. So they're all shifted the same. So like if A is 65, uppercase A is 65 in ASCII, lowercase a is 32 later. So maybe somehow, 32 later would be 97. Maybe somehow, I don't know, that has something to do with it. I mean, right, if we really wanted to, God, these videos are so long already. We could go back in and actually print out, right, because the way we did it, it multiplies the frequency versus all the vectors of what it could be, and did the dot product, and where is it here? We take the max score, and if I remember right, like if they were lined up perfectly, you got a dot product of like 0.66 or 0.06 or something. And then like all just random noise was like 0.25, 0.025, I don't remember which. And then we could see what was kind of going on. But yeah, that is interesting. I guess if anyone ever watches this video, and if anyone's ever listened to me ramble this far in on this particular challenge, and you know why it is that, like, I completely understand why we get challenge 20, the first character wrong. Makes perfect sense. I don't understand at all why we still get it wrong, but now we basically get it right. We've just got lowercase instead of uppercase. Unless, how many of these were there? Yeah, there's only 39. Maybe somehow we got lucky in that there's less of them. So what we do for, let me just do it this way because it'll be quicker. I was just kind of seeing what the first so, cause, so, but, I, so, thinking, I. Doesn't look like it's a lot of not even randomly distributed words. Maybe that played a lot with it, where this looks a lot more like, no, it's the same thing kind of though. All, to, of. I guess these are more of any word, right? Like of, and, or. Still would be wrong, but like that's going to be a different frequency than the first word of a sentence. So that might have a little bit to do with it, but. So you're better off with this maybe because it's more closer distribution. So what I'm trying to say is the first letter of a word might have a closer frequency distribution to the one we're using than the first letter of the first word in a sentence. So that might be why, I don't know if that's true or not. That also might not be true. But that could explain why we get it wrong here and right here. And it could also be, right, we're taking the max of those vectors. Maybe there's a couple really close ones and just sort of like it eked out close, wrong way here, right way there. But that doesn't explain to me why, unless there's something in the code that I'm not remembering because we did it so long ago, why it would work out that we get the right letter, but lowercase, not uppercase. And that'd be really funny if I'm just rambling on for like 10 minutes about it when it's just because I'm dumb and forgot something. Anyway, enough of that. Hopefully anyone who's watching this skipped it a long time ago. Yeah, so that's 19 and 20 done. Let me just double check and make sure that I've got these right. Oops. Okay, so everything's okay. So then we can move on to challenge 20. Sorry, actually challenge 21. So basically, we're just going to rip the code straight off of Wikipedia. So let's go again. Oops. Get rid of these. So MT19937 Wikipedia. Okay, so most widely used pseudo-random number generator, 32 bits, used a bunch of places. There should be. Okay, so based on blah, 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 blah. It's like we have a bunch of, excuse me, different variables. The series is the recurrence, so some future one is some other index XORed with, what is this U? Oh, so some kind of twist, ORed with an A. What is it? Oh, okay, so A is, okay, so we're getting the upper bits of something, concatenating with the lower bits of something, applying a transformation to it, and XORing it with something else, depending on what something equals, blah, 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 blah. Oh, we have 32 and, I guess that makes sense, 32 and 64-bit. So we initialize it, x minus 1, which is some shift plus, what is f? Oh, okay. Different f's. Oh, here we go. So implementation of constants. All right, so actually let's, we're gonna do it kind of like how we've been doing everything else, where we're gonna implement it. We're not just gonna like code it in challenge 20, because we're actually gonna be using it in these next coming challenges anyway. So we're actually going to create it in our utils. We'll have a mt1937 pi file, and then I'm pretty sure that we don't, like, I think everything we're do is just going to be the 32-bit, but just for both the practice and, I mean, we're going to implement it anyway. Let's go ahead and implement so we can use either 32 or 64-bit, because it looks like it's the same algorithm. You just use a different set of constants. So first off, let's just rip all this off, and then we're going to, let me clean up some of this stuff. Okay, so this is what we're building. Which right now is just pseudocode. So we'll use this to switch it into, this is the algorithm. We're just gonna make it Python, basically. And I guess let's look at it real quick. So we're creating some constant array of some size. We're setting an index. We have an upper and lower mask. Then we're gonna seed it. Here's, I guess, how we get the next random number. So if the index is greater than n, that's the transform. If we're greater than equal, so if we're greater than, it was never, okay, so we initially set it to 1 greater than n, and then we check, and if it's greater than n, that means it was never seeded. Actually, we'll just go ahead and get rid of this, and we'll make the default seed, if they don't provide one, be this, and then we'll automatically seed it when we initialize it. And here's our extract number. Oh, yeah, same function. Then we're doing a bunch of bit shifting and anding and stuffs. Oh, and we're returning, okay. So it's going to have a state that is different than the number. Okay, so we're getting something from the state, applying all this stuff to it, and okay, that makes sense, because I know one of the later challenges is like we're going to clone it. So that's okay. And then here's our twist. So basically then we want to have these variables. Do they give it? There was also an F. Here, let's grab this one. Okay, so let's think how we're going to do this. let's do like we did with AES, where we'll have in here, we'll have a new, and from that, I'll just make it temp right now. Oops. That is how we're going to create. So like we'll have, I guess I should, here, let's, class, we'll call it MT19937. And then we'll have our, oops. It's amazing how I sometimes just cannot type. It's weird because like I'm not, you don't look at your keyboard, but the fact that the way my mic is, I can't see my keyboard, and it really throws off my typing. Even though I'm not, I guess that just means I look at my keyboard more than I think I do. Anyway, blah, blah, blah. Then, okay, so here's what we're going to do. We are going to have a new, in here we'll give it like what version we want, like 32 or 64. I guess we'll have a default, and then we'll have a seed. Let's just int for now. I don't know if we'll want to do bytes or not. And then what it's actually going to return is, oops, yeah, that thing. It'll return this whatever version we're making. So like we'll do like how we did with AES, right? Depending on what we passed into new, it'll handle all of that. And then again, that kind of sets us up so that like code reusability, and if we want to change the way this is implemented later on, any programs we've written, it won't matter because they're still like, this is sort of the gateway into that. So if we make the gateway, I'm trying to think of the right words, but like basically any program we make that's going to rely on this is going to be calling this new function, and the program itself that we're going to use it in doesn't know or care or anything at all about what we name the actual class that we're using it. And like we can have, like how I said with AES, I wish if we'd have done more, we'd have done like multiple different ones. Like we don't got to know any of that. All our program needs to know is we just import, MT19937, and we call the new function and we tell it what we want, and it's going to give us that. And then we'll have a couple constants. We'll have a 32. We'll make these dictionaries. Constants. Oops. And we'll make a 64. Actually, I should do one and then just paste the other. So we'll have, this probably wasn't. If I were like better at videos, I would like do all this off camera, or ooh, just speed up this part in the video. Oh, am I getting, I'm kind of screwing this up. We also want a T apparently, and there's a UD and an L. And since we're dictionarying it, we want these to be and then it's a dictionary, so we want blah, and we'll put a little comma. Here we go. Let's just do this. Oops. Lame. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I think we lost BC. That was the one I think I screwed up. Yeah, BC. So then we need a C. Oops. ST. Oh, there was an F too. And here's the actual values they'll be. So let's, oh, I can't move this because the way I set it up. Here, I'm gonna open this up in a off-screen browser just so I can see at the same time what's going on. Okay, so, and then we had an F. All right, so now we'll copy that. All right, now we want to fill in these values. So I'm looking at the thing I have open, 32, 624, 397, 31, some hexadecimal number. So I'll just write it in hex. I'm guessing that's going to be for like the ands and stuff. They usually, so those numbers are written in hex because it's a lot easier visually to convert to binary from hexadecimal. Actually, maybe I should go over that so this isn't complete waste. Wait, U and D. Okay. Oh, son of a bitch. I'm not paying attention. I'm copying the wrong ones down. So A was this. U and D is this. They didn't have them the same. So yeah, here. So it's not a total waste. And then maybe you already know this if you're watching, and I'm just wasting even more of your time. But basically, so if you have hex, let's say you have 66A in hex. It's really, really easy to convert to binary because the way hex works, hex is 16 and a byte is, let me think if I'm explaining this. All right, a byte is 8 bits, and each one of these in hex is going to be, right, because hex, okay, here we go. Hex is the numbers 0 through, or hex is the numbers, 0 through 15. So there's 16 of them. So you can represent that with 4 bits, right? Because 2 to the 4 is 16. So the numbers, you can use 4 bits to get up to the number 16. Because with the 4 bits, we can represent 0 through 15. So each one of these characters can be represented in 4 bits, is 4 bits. So a byte is 8 bits, so every 2 characters is a byte. And the nice thing about hexadecimal is if I want to know the binary of what 6A is, you just do the binary of the first part. So what's the binary representation of 6 is just 420. Or no, wait, that's wrong. 0, 1, 2, 4. Yeah. Sorry, here's one I messed up. So 0, 1. So this place is the 8th value, 4, 2, 0, 1. And then to get, and this is how you often see it, we'll break it with a space. Then you do the value of A. So A is 10. In the hexadecimal A is the decimal, or is, the base 10 value is 10. And in binary, then it is 8, no 4s, a 2, and nothing else. So 8 plus 2 is 10. 4 plus 2 is 6. So we now know 6A in binary. The byte 6A is 011, 01, 011. You can do that for anything. So like OX, let's do E3. So again, you do the first part. E is 14. So that's 8, a 4, a 2, a 0. And then 3 is no 8s, no 4s, 1, 2, and 1, 1. So that would be, so you'll often see it, I'm just going to go ahead and assume. We're going to use this in our stuff down here where we're doing a lot of ands and stuff. They usually make those numbers hexadecimal, just kind of by convention, and then it's easier also to think about. Like when you think about you're anding something or doing stuff like that, you can almost, well, I'm sure a lot of people can when they do it a lot and get really good at it, you can sort of in your head see the binary from that. You could just as easily, so 6a is going to be, what would that be? 101 in decimal. Oh, 106. Okay. So you could just as easily write it as that and then do your and thing down there. But I don't know, then it just makes it harder mentally. Like take 106 and make the binary out of that. You're going to be like, that's a lot harder than doing it like just looking at 6a and seeing it visually. Because like binary, what was the binary for that? So you could also do, so I mean you could do it out, right? You like, so that's a 2, a 4, so that's 6, 8, 16, so 20. Wait, 0, 2, 4, 8, 16, 32, 64. So it's 64 plus 32 plus 8 plus 2. That's, I don't know, that's just harder to do in your head. Anyway. Yeah, I don't know if that helped or hurt, but that's what we'd be doing. So make sure I'm lining this up. U is 11, D is that, S is 7, B is this, another hex number. T is 15, and C is another hex number. L is 18, and our F is a different part, so I gotta find it. And then our other F here was that. And then our 64-bit ones is 64, N is 312. Oops. M is 156. R is 31. So R is the same in both of them. A is a much bigger hex number, which makes sense because we're doing 64 bits. U is 29. D is a bunch of 5s. S is 17. I'm probably going to end up putting one of these in wrong, and then when we go to like debug it later, this is going to be a bitch to find. Actually, I'm going to rearrange some of this too, because the way they are writing it in the one part is dumb compared to how they do it in the other. 37, and C is this thing. Oh, see? T is 37, and C is that thing. And then L is 43. And I'm going to swap up a couple things, because like they have W, N, M, R together. Then they have A, and then they put U and D together, which are together here. U and D, and then they have S and B together. So we want to put S there, S, then B, and then they have T and C, and then it goes to RL. Okay, let me just check these real quick. 34, 16, 156, 31. B ends in E9, 29, bunch of 5s. SB, 17, 7, 37. Another hex, 43, another big number. So then we want that same pattern up here, WNMR. A, we want our UD. And then we want SB, SB, and then TC, and then we are good. Okay, so we're going to take self, we'll take a version, we'll take consts, which is going to be a dict of, I'll just leave it as a dict. Okay, then tab this stuff over. Ooh, doesn't look like it lines up. Did I not line that one up? Tab it over. Okay, so we need to initialize. So we'll say self mt equals I for I in range. Oh, actually, first let's get our I don't know if this is the best way. What I'm going to do, because then when we're going to type all this out, I don't want to have to type like, so what I'm trying to think of is like, we could do like self const equals consts. And then anywhere where we want to use one of those consts, then we could just say self consts, and then the one we want, which was in. But we're going to be doing a lot of that later on. And what I'm actually going to do is do we'll just set up each one. So then later on, here we could just type self.in. I think that'll make the code easier to read later on. And this is another one of those spots where it's like I get really frustrated and don't know what to do because I don't know. That's trying to set this up is like, I don't necessarily like the way I'm doing it. And this is like, if I weren't in this video under like, oh God, this is being recorded right now, I gotta like just do something. I would end up spending forever going back and forth and trying to decide which way to do it. And it's just so much better to just go ahead and do something, get it down, and then you can always refactor and change things later. Like it does, like that's the only way you're going to progress, right? If like your ability right now is all you can do is write shitty spaghetti code, just get it to work. And then as you make more things and get more things to work, eventually you'll start getting better and better. And then, you know, hopefully like a year from now or 2 years from now or whatever, if I were that future me doing this right now, I might be doing something completely different because I've written, you know, enough of these, what I feel like is ugly and this is, I don't know. And I'll have come up with a better, more elegant way to do it. And I'm doing that now as opposed to like not doing all that stuff because I'm always just stuck here on this and I'm spending way too much time on every single project trying to make it perfect when I'm not even good enough to get perfect. No one's good enough to get perfect. So like just basically this long ramble is basically just to say, do the best you can, get it to work, and then you can always go from there. Don't stress too much. It's better just to have something that works than nothing at all. So we're actually just going to do all of these. So we're going to say self w equals const. So I'm going to copy all this. So we're going to have W, N, M, R, A, U, D, S, B, T, C, L, F. W, N, M, R, A, U, D, S, B, T, C, L. Although I guess there is some merit to trying to make it better, at least thinking about it a little bit, because otherwise, right, you're never, like, say maybe this is the stupidest way to like actually write all this out. Someone knows like, oh, why doesn't he just, I don't know, there's some bash shortcut or something I could do to like format all this beautifully like that. I'm never going to learn it if I don't ever try to make the process that I'm working on better. So you want to spend some time being like, this is ugly. There has to be a better way to do this. I wonder what that better way is. Now, some of it's just naturally going to come, right? Especially if you're in an environment where you're around other people who program and you're looking at other people's work and doing other things, you're going to see things. But if you're just like kind of like self-taught at home, doing your own thing, if you're not running across other code a lot, you might not, you might need to spend a little bit of time thinking about it. Like, is there a better way to do this? Like, but the extreme of either extreme is bad. Don't go to the extreme of like I do, where it's like you stress and fret and never get anything done because you're stuck trying to figure out how to make your shit bomb not a shit bomb. But then also don't always just write shit bombs, because that's what you'll always end up having. You're never forcing yourself to come across a better way to do it. So yeah. Anyway, so then we're going to have our index is equal to n plus 1. And then we've got a lower mask and an upper mask. Let's see. That's just a binary number of r's or ones. So what that means is basically this is just, so r is 31. So what this basically doing, whenever you see a shift, so like if you have, I'll do it in text a little easier. So if you have 1 and you want to shift it over by 1, what you're going to have is 1, 0. You shift 1 over by 2, you have 1, 0, 0. What it's doing is just taking the 1 and shifting it over, and then everywhere behind it gets filled in by a 0. So when you have this, what they're doing is you're shifting 1. It's the same thing as multiplying by 2, actually, as well. So 1 shifted by 31 is the same thing as multiplying 1 by 2 to the 31, which if we look at that at binary is going to be a 1, is going to be a 1 followed by 31 zeros. Well, we want, yeah, that is 31 zeros, right? I'm like doubting myself now. I mean, it has to be. We shifted it 31 times. So that is 2 to this number here is the same as 2 to the 32, right? We've got 31 zeros and a 1. So that's the same as 2 to the 32. Oh, that's 2 times 30. We want 2 to the 32, right? Oh, why are those numbers not the same? 31 zeros and a 1. I guess I'm wrong. What I'm trying to say is basically that 1 shifted over by 31 minus 1 is going to turn all those, it'll get rid of this 1 and turn all of those 1s or all those zeros into a 1. So you'll actually be left with 31 1s. which is why it's called the lower mask, because when we AND it with anything, so like an AND, so if you're doing binary operations, the only way to get a 1 is if they are both 1s. So 1 and 1 is 1, but 0 and 1, or 1 and 0, or 0 and 0, or all 0. So the only way, basically, you can think of it as a mask, like if we wrote this out like, I don't know, 1 0 1 1 0 1 1 1, and we're ANDing that with 1 1 1 1 1 1 1. The way you can kind of think of it as, so I'm writing it like you would, sort of like this and this equals this. It just sort of, they call it a mask because it keeps all the ones where they're supposed to be, right? So this and this, you get, so like actually, so the way I would want to write it then is if we had a number like 1 0 1 1 1 0 1 1, and we wanted to know what the lower 8 bits were, the lower byte was, we would do, actually I should do it like this. Woo. Right, and you want to know what the lower 8 bits of this number is, you would AND it with 8 1s. And then what you'll get is, see, all these go to zeros, and then you get what this actual top number is, right? Because it'll be a 0 whenever there was a 0, because you're wanting it with all 1. So it's the only place this is 1 is 1. So you just get this number again. So the way to get, if you want 8 1s, is to raise it, shift 1 over 8 times, right? Because then you've got a 1 and 8 zeros. And then when you subtract 1 from that number, you get, right, it's just like normal arithmetic where you can't subtract zeros from 1, so you have to carry. So you're going to change this to a 0 and make that a 1. And then it just like carries the whole way down the line, and you end up with 0, 1, 1, 1, 1, 1, 1, 1, 1. You end up with 8 1. So again, long-winded way to say that's basically what they're just doing here is getting, and we could actually change this because R is the same in both of these, right? 31 bits, 31 bits. We could actually, for clarity, just put in, so 2 to the 1 to 31 minus 1. I mean, the hex is going to be a bunch of Fs. And then yeah, so 7 is the binary number 0 1 1 1. So we're going to have, that's why it's a 7, because this would be 32 bits, right? Because each one of these is a byte. So, whoops. There's 1 byte, 2 byte, 3 byte, 4 bytes. 4 bytes is 32 bits. We want 31 ones, so we need a leading 0. So that's why that's a 7. So let's actually just go ahead and make this hex, because it'll just be easier. Oh, I already had the OX. And then I'll just leave right now as a comment in case for some reason I realize I'm dumb and we need that. And then our upper mask is the lowest W bits of not lower mask. Okay, so like the upper mask, so right now we had what, 0 and 31 ones. This isn't 31, but we'll just say that's it. So the upper mask, when we're working with the 32-bit, they just want that upper bit, that 1. So the upper mask would be this. But in 64-bit, the upper mask would then be, right, there's 32 ones in front of that. So again, this isn't the actual right amount, but your upper mask is going to look like that. So basically what they're saying, why they're saying is not lower mask. So if our lower mask is this, not is just flipping everything. So it's 1 and all zeros. And then if like we were only coding the 32-bit version of this, we could actually just make our upper mask what this number would be in binary, which would be an 8 and all zeros. Right, if we do, let's do the not. So in Python, the tilde is not. We'll do the not of the last number. It should be 0x8 all zeros. Oh, I can't do it on a string. So we'll do the not of this. Oops. And then it's because it's got, so the reason it's negative is because the sign bit is the leading bit. So since in binary it would be 1 and all zeros, it reads this as, and I actually don't know what it'll look like in hexadecimal. I don't know how. Okay, it's the same. It just puts, so it's 8 and all zeros and it puts a negative. I don't really, since Python doesn't have like, I don't know how that it works under the hood in Python, where like in other languages you have to worry about like integer overflow and stuff. Like Python, it's just arbitrary number long. So I don't actually know how it represents like negatives and all that. Anyway. So the way we want to write this then, since we actually want to deal with both 32 and 64, is we need to make it more generalized so that so we could do, there's probably multiple different ways to do this. We want here's what we could do. We could do 1, we're going to shift that 1 over by the word size. And then we'll add to that the lower mask. I'll try and explain this after I do it. And then we'll and the whole thing. So what this would be in the case of, say, 32 bits, we're going to have a 1 and 8 zeros, 8, 16, 24, 32. So we're going to have a 1 and 32 zeros, and then we're going to add the lower mask. Well, we already said that the lower mask was, didn't I show the binary of that at some point? Yes. Oh no, that's, here, let's do it this way. The binary of that is going to be this, 31 ones. So we're going to add 31 ones to it. Right, so when we add it, what that is going to equal is 1, 0, and all these ones. Right, so top plus bottom equals that, right? So we have a 1, a 0, and 31 ones, and we want actually to have a 1 and 31 zeros, and we want to get rid of this one. So when we not it, it's going to change that 1 to a 0, that 1 to a 1. So when we not it, like say we're going to not it, I'm not going to go right out, but basically it flips everything. So in the case of now W, when it's, we're going to shift that 1 over 64, so we're going to have a 1 and 64 zeros. we're going to add our lower mask. Our lower mask is still the same. So now basically we're just shifting everything over. And when we knot this, it's going to turn all of these into 1s. It'll turn that into a 0, those into a 1s, and all of these into a 0s. And that's actually, oh, I didn't write that right. That is actually what we want. We want this to be our upper mask because we want these upper 32 bits. So hopefully that makes sense. And then we're going to go ahead, so we don't deal with this error here, we're going to automatically, I set the index. Oh, we need the, here, let me move this down. Makes more sense to me. And then we'll move this down. Oops. Because these are kind of our main constants, and then now this down here is sort of the actual, we're setting up the initialization. So here's going to be our state. So it'll be 0. We'll have an array of length n, and it'll be 0, 1, 2, 3, 4, 5. That's what it'll be as per what they said to make it. Then we set the index, and then we're going to go ahead and we'll have it called seed empty because that's what they call it. And then we'll pass in, we'll pass in the seed. So in our new function, we'll actually make it, because they said that default is 5489. Oops. And then we'll go ahead and seed it. So it's automatically always seeded, which means we can our seed is an int, and we don't return anything. So index equals n equals self.in. We set the initial thing in the array to be equal to the seed. We don't have a self seed. Maybe we should make one so you could always see what it was seeded with. I don't know, we'll see if it comes up. And then we're not going to have, oh wait, the error comes in the case of when we actually extract. Okay, so here we're just going to have, we set the first index in our state to be equal to the seed, and then we're going to perform this action on all the other arrays, which is what it was from, it's going to be, we're going to perform this. Each index in the array is going to be equal to the previous index XORed with the previous index shifted by the word size -2, multiplied by f, and then the position gets added to it. So we will say for I in range self.in, that'll go from 1 to self-in. We're setting we're setting that position equal to the lowest W bits of self F multiplied by the previous index XORed with the previous index right shifted by W minus 2 plus I. So then we want the lowest bits of this. So we will take that whole thing it already is wrapped. And we will AND it. We want the lowest W bits. So we want to AND that with 1 shifted over W times minus 1. I should probably just make a mask because I think we want the lowest W bits later on too. Lowest W bits. We can always, let's just go ahead and write it out the way they have it, and then we can always try and make it better if we need to. Okay, so that should work now. So that seeds it. We're performing this. This is how we're actually going to get our next random number. We don't give it anything, but we are going to return. I have to add. I always forget to add myself. It'll be interesting to see how many errors I get when I go to run this. There's got to be. This might end up being like the worst all time. So here's where we're going to get rid of this one, right? Because we know no matter what, it's always going to have been seeded. So we don't need to worry about the fact that it's not technically even we don't have to start it at n plus 1 because we're always running seed and it sets it to n, but whatever. So we do need to have our if our index is greater than or equal to n, we are going to run our twist. I'm underscoring these because we want to say that these aren't supposed to be callable by outside. Like these are sort of like inner functions. The only one you're going to call with this when you're using this implementation is just the extract number. Everything else is just behind the scenes stuff. So if we are, we'll twist. And then otherwise now we're going to have, we start out with y equals our index. And then we are going to perform all these operations. We'll be XORing. Here, actually, let me go ahead and do it this way. We can just replace every instance of XOR with the actual key. We're doing it self.u, self.s. And we can see DBC, these are going to end up being the binary ones. DBC, yep. I should have replaced it and while I was at it too. see. Then our index is plus, we're going to add 1 to it. And then what we do, so that means it increments it. So the next time it goes through, it'll check. If it is at the last one, then it runs the twist. Otherwise, it's already ready to get you the next one, and it goes ahead and grabs that from the state, performs all the operation, and then we are going to return the lowest W bits of Y, which will be the same thing as what we did before, which is we're ANDing it with this. Y and lowest W bits. Yeah. So now we'll do the twist function. Again, it's private. Self. We're not returning anything. For I from 0 to n minus 1, so that's the same thing as for I in range self.in. We're going to have x equals self and the upper mask. Oh, and we're just adding plus. Is it actually a plus? Plus the previous index mod in mod self.in. We're adding that with the lower mask. And then we have this temp variable. We're shifting off the last bit. So like how when you shift to the left, you add zeros falling behind. Like when you shift to the right, everything. So like if your number was 1101. Yeah, let's just do that. And then you were to shift this number to the right 3 bits. Like so you shift, basically the front 3 are just gonna, you can think of it as they fall off a cliff, and its zeros get added in behind it. So it's kind of the opposite thing. So you lose information. So we're shifting this to the right. We're dropping the last bit on this temp one. So the temp one is basically the original. So when you shift to the left, you're multiplying by 2. When you shift to the right, you're dividing by 2. So XA is basically X divided by 2. And we're checking if X is odd or even. Oops, if X, I forgot what it was. Oh, okay, that's why I'm confused. It's still below. I was like writing it as I was looking at it, and I want to actually change it. If X modulo 2. So if X is not even, yeah, if X is not even, then our temp one, which was X divided by 2, is now X divided by 2 XORed with whatever our magic number for A is, which varies based on what version we are. And then that position in the state, we're still in the main loop there, is equal to some future position modded by n, so it loops back around if we go over, XORed with this, what's essentially x divided by 2 XORed with A if x was odd. None of that really makes sense to me, but there's obviously like mathematical reasons for why they're doing this. I just self-index equals 0. So when we're done twisting everything, we set the index to 0. Make sure everything's lined up right. And that should be it. There's probably all kinds of formatting. So now we will have, let's do a little bit of error checking. If version is not in 32 or 64, we'll throw a value error. Let's say version must be either 32 or 64-bit. Then we'll get, right, because we have to pass in the constants, so we will say our const is going to equal constants 32 if version equals 32. Otherwise, it'll be set to constant 64, and then we will return our instance with what we do, version and then version const. Oh, we need a seed too. Version const seed. Yeah, so if they don't give us a seed, it's automatically set. Version const seed. Version const. Yeah, we need to add room for a seed. Seed, which is an int. Where else do we use seed? We only, we do. Maybe we should just set it to self seed, and then, because we're only seeding once. Technically, really, we could get rid of, don't even make this a function and just add it in right here, and it automatically does an initialization. But I'll go ahead and keep it separate, because then it just makes it easier to read. We know what we're doing, like the specific call is to set everything up. All right, I think. All right, let's see if that even compiles. For I in ring, okay. Line 61. I forgot to put that. And I did. Ooh, what did I do wrong here? Oh, we have double ands. All right, so no more typos. Only two formatting errors. That's kind of surprising. Now we need a way to check our implementation. So the best way to do it really is let's just find one that already works, and then we'll compare them. So if we go, let's do int 19937, testing. Let's just try that and see what we get. So it looks like per actor and let's do Stack Overflow. Okay, they have a website. Oh, and test output. Sweet. Specifically 64-bit. So they have different test versions. So this looks like the 64-bit test. What's it seeded with? Is it the default seed? Let's just go to the website. What do we have here? We want that. Is this? Let's see what this is. Yeah, so here's what we want. We want the test. Yeah. So our out text. Okay, so that's what is test C. Come on. All right, you know what I'm gonna do? I'm gonna pause this real quick, and then I'll sort out what file to use and everything. There's no reason anyone should be forced to watch me do this. So I'll be right back. Okay, I'm back. So I found the code that they use to generate the test outs, and it's C code. And so I was trying to find what the what seed they used, but it looks like this wasn't in the Wikipedia, or at least I didn't see it when we skimmed it. There's two different ways you can seed it. So there is this, where is it? Oh, okay, so initialize genrand, and you're giving it a seed, but then there's this initialize by array, and I forget where I read it now, but it was saying that this method is a little better. I'm not really sure why, but anyway, ours is the normal way. But what I'm trying to get to is their test program was generated using a init by array, and we want to use a init by seed. So what I'm gonna actually do is we are going to make, I don't know C very well, but I feel like I know enough to do what I want to do here, which is, let's say MT19937, we'll call it that, and yeah, this is a 32-bit version, so we're going to copy everything and paste it in here, and then we'll do the same thing with 64-bit version. We're actually going to compile our own so that we can set up, we can get it to output test data for what seed we want to use. And maybe I should just not put this in the video and just be like, here's the test data I created, but I don't know, I thought it might be interesting to screw about with a little bit of C here. All right, so now we can get rid of a lot of this stuff. Let's go keep it for now. So this is our, basically we're going to do the same thing here. But so we are going to, let's Sorry, let's muck about a bit. We're actually we're gonna compile this into C and run it from the command line, and it's gonna generate output for whichever seed we want it to be. So let's actually do it. So we're gonna do some C here, and we're going to have it read command line arguments, which we're gonna do like this. Now again, oops. It's argv array. I don't know C very well. This is going to be the number of command line arguments, and then this is the array with each argument. And then we're going to write. We're going to have one of the arguments we'll pass in will be the file name, and the other one we'll pass in will be what seed we want it to be. So we can go ahead. And we won't be using this because they're using that to init the array. So using init by array, we're not going to do that. So we're going to have unsigned long for the seed, and then we will have I think it's file. That's going to hold our file that we're going to open. And then we'll check to make sure we're going to want to have 2 command line arguments, which means argc needs to be equal to 3 because in the array, the 0th position is the name of the program. So we'll have if argc does not equal 3, then we will print out an error. So it's f printf. We'll print that to standard error, and we will print run with. Do some formatting. Run with seed. And we're using the %s will be a placeholder for the name of the whatever it was named. So that's going to print out run, MT919 blah 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 seed file name. So it's like if you screwed it up, it won't run, and it'll print out that error. And we're going to return 1, which I got to remember to do semicolons again. Is going to, that's like a return with an error. So it'll exit with error, and it's printing out standard error. I don't actually know. I think you could return standard error and return 0. I don't know. I just know return 1 is, I don't know. I'm pretty sure that means return with an error. And then what we'll have the name of our file is going to be, or the file we're opening. So we have a pointer to the file, and it's going to be the 3rd argument, and we want to open it. I can't remember and see if it matters if it's double or single quotes, so I'll do double. We're going to open it in write mode, and then we need to convert our seed. See, these are characters. So these arguments are coming in a string, so we need to convert our seed to an unsigned long because that's what it uses up here. And we're going to do that with string to unsigned long. And it's our first argument we give it, which is the second one. And then we want that base 10. So what this does is, since we're giving it a string, if we had a variable, if we put a variable in here, that's where it would output all the non-number stuff. So like if we had, I don't know, 52 is my favorite number. It's not, but whatever. And we passed it to string to unsigned long. It'll convert 52 to unsigned long, and then it would print out, or it would send to wherever the variable here you put it, be like space is my favorite number. And since we don't want anything, we're not sending it anywhere. And then, So we don't want that. And then we are using, we're going to init genrand because that is, let's even just go ahead and, should probably just comment it out, but we're just going to whack it. We're going to use init genrand because that's the seeding method we want to use. So init genrand. Do we need init and length? Unsigned long. Oh, it's because I'm changing a different method. We're just giving it the seed. And then I guess we can keep that printing out 1,000 outputs. Let's go ahead and give it the name of the file to, I guess I should have used, where is my, having a stroke, I can remember where my percent key was. Okay. And then we, yeah, so then we'll print to this file. Let's put the seed on the first line and then the output of everything else after it. So we are printf. We're printing to fp. We're going to print seed equals, and then we do it backwards, which I don't know why. Like if we were going to print a unsigned long, we do LLU. Again, I don't know, see well enough to know why we do it this way, but I can pattern match with the best of them. So we'll print our seed on the first line, and then we'll print 1,000 outputs of, yeah, let's change the way we do this, because we're printing to the file, not to the terminal. So let's do, I think that is making the unsigned long 10. They'll all be 10 long, 10 digits. But let's just print our unsigned long 1 on each line, because then when we import it, we can just do chop it up by lines. Genrand 32. Yeah, so they were spacing, so after every 5th one, they printed a space or a new line. We don't want that. We're not even doing that. And we're returning 0. So that should work, I believe. So let's see if that'll compile. So we're going to compile it with GCC. We're compiling MT. We're compiling this one, and we will write it to file, or we'll write it, we'll call our program 19937-32. And then this should give me any compile errors if there are any. Implicit. We need to import or include. This is how it gets the name of the functions you're using. So we're using standard lib. And then, what was the other error we got? Oh, I didn't use another semicolon on 162, which will now be a little later. Boop. So basically, it didn't know what the function, where is it? string to out is, because it didn't have the header file that tells it that's a function. Okay, so it compiled. So what we should be able to do now is, well, we have to make it executable. We should just be able to run it. And then I said it was seed file. Here, let's see if that even works. Yeah, so we don't give it, it tells us what to do. So we want the seed. Let's just use, I don't know. It doesn't matter really. 1, 2, 3, 4. And then we want it to write to file. Oh, do I put it in parentheses or not? Here, let's just write it to 1 mt 19937 32. We'll call it out, because I think that's the name that we're using for their test stuff. So we should have a file called, that will be the seed, and then a bunch of lines. Yes, we have seed and then all the lines. Sweet. And then we'll just move it to our resources. So now basically we want to do the exact same thing, because we want to, right, because we programmed to do a 64 and a 32-bit. So we want to change this and have it work with 32 bits. So the things we need to change are, hopefully I don't get myself in trouble copy pasting. Let's make sure that these are named the same. We'll just whack this. We can also whack all of a bunch of other stuff too. But yeah, it's init genrand 64 and then genrand 64 int 64. So init genrand 64. Genrand 64 int 64. I think that's all we need to, oh, we need the standard lib too. Include standard library headers. Let's see if it compiles. So we'll compile mt193764. We'll compile that to mt193764. And then we will make it executable. And then we will run it. Let's make our seed longer this time. We'll do, there, that's the seed we'll use. And we'll write it out to, what do we call the other one? Out. And then we'll move to resources. There we go. So now we can write, we'll use challenge 21, we'll write our test program to test it and make sure it works. So we're going to import from utils, import, oops, we're importing that. Then we'll have our if main blah blah blah, and we're gonna do here, let's just do Yeah, let's just do it like this. We'll just run test implementations instead of writing all the code in main. And then we'll have, so we'll test, let's have test info 32. We'll parse, we'll do our standard parse test, or how we've been writing our parse stuff to get all the data. And then we need to create it. So we'll call it, oh, you know what I also want to do? Because I don't like how this is extract number. Let's call it, what they call it in the C, it was, do I have that open still? Yeah, what did they call it? What's a better name? And then it'll be more in line with. Yeah, genran int 32. So we'll call ours just genran int. Genrand int. Yeah, I like that better. So we're going to create RNG32. We're getting a new MT199937. Let's see, we needed to give it a version and a seed. Here, we'll make, let's just do it as a dictionary, I guess. We'll pretend test info, well, we'll make test info 32 a dictionary. It'll hold the seed, and then it'll hold all the test info. And then we'll test it. So we'll give it whether did it pass or not. We'll have another function called where we'll actually test. And we'll pass in what we're testing, and then what we're testing it to. Let's call it output. And then we'll do the same thing for 64-bit version. Should just copy and paste it, but screw that up. So 64. 64. We'll call it past 64. Past 64. And we're testing it with RNG. Oops. 64 and our output test info. And then we'll print out some snazzy graphics. Testing MT1937 implementations. Then we'll print 32-bit test. And we'll print past if past 32. Else, why is it not highlighting it right? Oh, because I'm an idiot. Past, if past 32, else, it'll print out failed. What? And then we'll do the same thing. The 64-bit test. Past, if past 64. Why wasn't it giving me? All right, I must have named that wrong. I didn't, though. I don't know. That's going to cause an error later, I bet. There's something's not right. Failed. Now we just need to write our, what do we have? We had parse test file. Takes a file name, which is a string, and it's going to return dictionary. And then we'll have our actual test, which, what did it take? It took an RMG, which was a I guess you would need to know what's behind the scenes if you're going to do type checking. There's probably a better, like we just, I don't know. I don't know Python well enough to know what you should do in that situation. And I mean, obviously I'm not using a linter anyway, so like type checking doesn't matter. I mostly do this just because it's way easier for readability. This is what everything should be. It's going to be a list of integers that we got from when we parsed it, and it's just going to return true or false. So that's F. Seed is going to be the first line. We want to convert first line. We want to split it on, what did we say it was? Seed equals. So we'll split it on seed equals. Yeah. And then output will be everything else. It will be the integer that is each line for line NF. And then we're going to return a dictionary. Seed, output, output. And then this one, how we're actually going to test it is see, we have an integer list of 1,000. It's what it should be. So we could say generated equals, we'll do list comprehension. We'll say for, we use underscore because we're not actually going to hold a variable. And however long expected is, that's how many get, or gen, what do we call it? Gen rand ints we're going to call. Oh, over there. For in range generated, and then we can just compare generated has to be equal to expected. Return true if generated is expected, else false. Actually, that's dumb. I was at 5 myself. We can just return that, and it'll be true if they are the same, and it'll be false otherwise. All right. I think that's it, although I don't understand why it wasn't highlighting past. I don't know. So I feel like there's no way this is going to work, but all right. Moment of truth. Yeah. Genran int name in is not defined. Oh. right, well, our program ran, but we are not getting the proper outputs. So that means our algorithm is not working right. Well, potentially. I mean, that's the most likely scenario. So we'll start with that. Let's make sure we got, let me open up what the variables were supposed to be. Where'd my browser go? Let's make sure we got these right. 32, 624, 397, 31. F 11, F 7, 15, that, 18, that, 32, 156, 31. That's right. 29, D, S, B, T, C, L, F. Okay, those are right. Do we make everything right here? Yes. Maybe, I know this isn't wrong, but let's, okay. I can at least feel good about that. Let's see, so our lower mask is that, our upper mask is the knot of, we shift it over, we add the lower mask, and we take the knot. That's right, I'm confident in that. This doesn't actually matter because we're rewriting everything, but it's still the right length. We set the index again, that doesn't really matter because we're calling the seed right away. We have our seed, 0, self in, and then the initial was set to, got an XOR. I'm just comparing it with the pseudocode. I have a browser open on my other monitor. When we generate a random integer, if the index is greater than or equal to n, we've gotten to the end, so we need to twist. We grab it from the index. We right shift by U, and we end with D. We left shift by S. And we end with B. We left shift by T and end with C. Right shift by L. We increment the index by 1. We get the lowest W bits. That all looks good. And self upper mask. Oh. Yeah. We don't have, will that matter? I don't think it actually parentheses would matter here though. Because I think order operations, it would still do and this first and then do this. Yeah, so I don't think that even matters. We're going to add 1. If it's not equal to 0, we XOR with itself. I plus n modulo n. And when we're done twisting, we set it back to 0. I feel like that should work. Well, I guess order operation, I don't feel like that shouldn't matter. Huh. Well, there we go. I guess all in all, that's not bad. One tiny error. And I randomly picked a seed. So I mean, like if I feel confident enough that it's fine. Otherwise, you'd want to test it against a bunch of different seeds. But I mean, we tested it versus the actual official C implementation, so we should be good. So yeah, sweet. Challenge 20. So excuse me, challenge 21. So now I can get rid of all this stuff. Okay, so this one is going to be pretty easy because it doesn't, what this basically is, it doesn't matter at all. Like the crux of this challenge isn't based around the fact that whatever this implementation is, you know, that's a Mersenne twister, like there's no flaw in it that makes this vulnerable. It's basically, this challenge is just going to show you like why it is so bad to use time in order to seed a random number generator, or at least time in the fashion that we're using here, which is going to be per second or in seconds. So we're on challenge 22. So let's go ahead and whoops. So basically, they want us to wait a random number between 40 and 1,000 in seconds. So somewhere between, I don't know, less than a minute and 15 minutes, more than 15 minutes. Then to have the random number generator get its seed with the current Unix timestamp, and then wait another random number seconds. So the reason they're doing random before, grab it, random after is because then we won't know at what point, you know, say we sit there for half an hour, we don't know, well, let's say we sit there for 15 minutes. We don't know if it waited 40, grabbed the seed, and then waited 15 minutes, or if it waited 5 minutes, grabbed the seed. You know what I mean? Like we can't, basically this is just designed so that we don't know what the actual seed of the random number generator is, but then it's going to show that like it doesn't matter because the space is so small that we can just check it. We can find it. Yeah, return the, okay, so let's just, this, I'm trying not to overthink, maybe we can blast through one short instead of me like always waiting, taking forever. So we're going to import time and random. We're going to from utils import our Mersenne twister implementation, and then we'll just have a if. And I'm just going to simulate it because clearly, I mean, I guess I could speed the video up and play some sweet music and I don't know. But we'll just simulate it because that's how we're going to do it. You know what? We're going to simulate it, but then I'll go ahead and do the thing and we'll just start working on challenge 23 while it runs in the background. So let's have a, we'll call it get seed simul. So what it was, it wanted us to get a random integer between 40 and 1,000, and then add time. So if you look at time, I'm pretty positive that's what the actual Unix timestamp is this time. You see, this is the number of, I think it's the number of seconds since like Unix was first made or whatever, which actually is, I'm old enough to remember Y2K, but there's actually supposedly a new Y2K coming, because if you look at this, here, we'll call it T, let's get the int version of that. That is of size, binary of T, we want to chop off the 0B. Right, so that's 31 bits. So supposedly there's a bunch of old programs written that use this function, and so what's going to happen when the Unix time is going to be 32 bits, it's going to overflow all these things, and I don't know, airplanes will fall out of the sky and whatever. Anyway, semi not interesting sidebar. So then we're going to add to it another rand int between 40 and 1000, and right now this is a float because as we saw it was, so we're just going to convert that to an int. So basically this would be the exact same thing as if we, like, whatever seed we get is going to be some random number we don't know, that's going to be, I guess maybe I should minus it, like, so you're going to wait. So when the program starts would be, it could be any time between here and end. So it's actually, it'll be seeded with time in the forward, but basically what I'm trying to not explain very well is it's effectively the exact same thing. We know the start and end, but we don't know where in between the seed came from. And we can show that that's just a laughably small space to check. So then we will have a crack seed. Let's do crack seed symbol because it'll be different than the other one we're going to do. And we give it, should we just have it grab time? Yeah, since we're simulating it, whatever, I'll just get it at, so seed equals int time. Right, because we know it's going to be in the future the way we're simulating it. So for this thing, I don't need to worry about, there'll be a short enough gap between when these two things are called that this, I mean, we're talking fractions of a second, and we know it's at least 40 seconds in the future. So then we can just, we're going to have to target because we need to know what it produced. So we'll have a target integer, and let's actually have it return the seed. So we'll just say while true. Yeah, because I don't have we'll need to create a new one every time. We'll test this for 32-bit seed, and then if gen rand int equals the target, then we know we found the seed, so we'll return the seed. If not, we increment the seed by 1. And we're basically just going to brute force this, and we'll check all the seeds that in the possible interval it could be. I mean, we're not actually doing an interval because we're simulating it. But anyway, you'll see that it's laughably bad. Should I do a different test? Yeah, let's just do it here. So we'll say secret seed equals get seed symbol. That's returning our seed. Then we will create our 32-bit. I guess I should have, did I do that? Did I make a default, or if we don't? Oh, actually that's probably not. Because if you just, we're saying that's optional. Yeah, how does it know which? I should probably redo this. I mean, it's working only because I'm manually passing it in. Since we set defaults for both, that's not very good. I should just do like args or change it so that it's or I could do quarks and you minus at the version. Let's just make it so that you have to declare a version. We won't have a default. And then that takes care of that. And then I don't think that broke anything. Yeah. So you have to give it, like, we could go back and fix this, right? So that you could, if you just called new with nothing, it would default to doing a 32-bit with that seed, where now we have to explicitly state what version. The way we'd fix this then is either make one or both, just pass in args. But anyway, an easy challenge, and I'm still making this like way too long. We're giving it the secret seed, and the first one we get is generate int. And then now we want to try and crack it. So we'll say cracked equals crack seed simul, and we're giving it our target, which was the first one generated. And then we'll just print, do like how we've done on a bunch of them. Did we crack it? Cracked equals secret seed. And then we can print what the actual secret seed was. And what the cracked seed was. That way, if we're wrong, we'll see how far apart. Well, actually, this won't tell us anything. But I guess if we got one that was like letters or something, we'd know somehow we screwed up really bad. That should work. This might be a rare first time, although I was not paying much attention, so there's probably still some typos. Oh, no, sweet, worked. So basically you can see, right, in that kind of gap between, there's a 30-minute potential gap, which is only, there's 3,600 seconds in an hour. So, I mean, it's not even an hour. We're checking less than 3,600. Like here, let's see how many enumerations we're even on average kind of doing. I equals 0. And then let's print I. I mean, we went through 300, we had to iterate through, they were hardly, I mean, blink of an eye, we're doing 1,000 checks. So like your seed really has to be, right. So even if, like, say you knew that somehow the seed was made in the last day, that's still, so there's 3,600 seconds in an hour times 24 hours, 3,600 times 24 hours. I mean, that is, what is that, like 16 bits or something? More than I thought. So 19 minus 2, so actually let's go 17 bits. So I mean, that is, spoiler alert for a future challenge where I think we're going to, I think it said it was 16. So if your seed's basically created in the last day, I mean, you can crack it really fast. Well, not really fast. I mean, that might actually take, depending, well, our implementation probably isn't the fastest. We're doing it in Python, so you lose speed there. But I mean, like, built for speed and on a good computer and optimized and everything, you could probably, I mean, 16 bits is laughably tiny search space. So like, basically what it means is you should not be using the integer of time for your seed generation. And then just for fun, let's go ahead and do, let's do, we'll call it time sec. And then we'll actually have our secret seed equal time. Oh wait, no, we don't want to do it this way. We want to, let's do it like this. Get seed time sec, and then we'll actually, I think it's sleep. Sleep, a random amount, between 40 and 1000. All right, I should pay attention because I don't want this to run for half an hour and then I find out I typoed something. And then we'll get the seed as time. Then we will add to that seed oh wait, no, we aren't actually adding to the seed dummy. We're just repeating this. I guess I could cheat and make the wait potentially not as long, just to see if the program works. But I guess, like they said in the challenge, that kind of takes the fun out of it. And then we will return the seed. So our secret seed is going to be get seed time sec. And then we'll create our pseudo-random number generator with that seed. We'll get the first integer it spits out, or gen rand int. And then now we'll have, we need a different crack, right? Because this starts at the current time because we were using the simulation, but keep those together. Not that it matters, but oops. Here we know the actual seed was created at some point in the past, so we actually want to decrement. So we'll say like crack seed time. Yeah, we're not going to use this later. So I was just trying to think if I should try and actually make it a more explicit name so we know. But whatever, this is just for goofs. We'll take a target, which is an int, and we'll return an int. And what we're going to do is basically do the exact same thing. Get the current time. Yeah, I could probably just combine those. Whatever, I'm doing that thing where I'm like caring about something that I'm basically just reading exactly what I wrote above. The only difference in this code is now we're decrementing. Like before, we knew the seed was at some point in the future. you could use that function of say like, you know, I know that seed was created sometime yesterday, or actually I could say, I know that seed was created like, I don't know, 3 months ago on X date. I could start it, or I know like the seed has to be later than this time. I could run it on this one and it'll start at a time and go. Here, let's do it. Just crack seed, time, start, and we'll call this one crack seed, time, end. These aren't very good names. This one's like if you know it had to start after. This one would be like if you knew it had to be before, basically. That's what I'm saying, because this one's going to decrement and the other one increments. And it probably just a much better way to like combine those into one function, but whatever. And also you'd want something like this will run infinitely, where we'd want to have something on it. So like we're not potentially hanging our program up, or even just some feedback, so we know what was going on. So what did I say time sec was? We first, so now, oh yeah, so actually this is, so let's give it a start seed, because here we're actually, this would be getting a future, because we're calling time right then. Here we would actually, since we want to start it from some time in the past, we would tell it what time to start. Where this one, I guess I should do it the same way, where like maybe I wanted to, I know it came before some day 5 months ago, I'd want to pass in what the end time was. So now I need to, when I call, where is it? We get the seed. Where am I? Oh, here we go, cracked. So we know it's in the future. Here's where we can pass in time. Right, because we know it's after the current time. And then here we will equals crack seed. I don't have that anywhere still. Or is that just what did I say? Time start. And we do the same thing where we're going to pass in the current time in integer form. And the target was first. And whoa. Let's repeat the same line. It's kind of dumb that I have it split up into different methods, whatever. Because we're just doing this for a goof, so let's run time suck. And then we'll basically just run it in a separate window, because we don't want it, because it's gonna be actually, so let's add just so we know it's actually doing something. Where's our Tom? There, that way. here, we'll say and then we'll find out in somewhere between 2 minutes and 35 minutes, 40 minutes, whether or not I have a stupid typo somewhere. Or we can find out a lot quicker. Line 13. Oh. Let's just do this. Seed equals start. And then I think we need to do seed equals end. All right, so our first one that we simulated ran just fine. Now it's in its busy sleeping mode. Basically, we've solved this challenge. So let's just move on now to challenge 23. Yeah. All right, we're going to clone it from its output. Operation just transfer in the reverse order. Oh, okay, so they're saying here is, so I'll just talk about the 32, but I guess we'll go ahead and write this to do both, or test it versus both. So this state array, which was in the 32-bit version, is 624 values long. In the 32, or the 64, it's 312, and the 32 is 624. What happens when you actually get a random number is it takes that number that's in that index of the state array, and then it performs these operations on it and returns that. Well, this challenge is telling us that these operations are invertible, so we can actually take the random number it gives us and work backwards to figure out what the actual value was in the state array. So we know there's 624 variables in the state array. So if we run that function, we get 624 random numbers, and then each time we reverse everyone it gets us, we can actually reconstruct the entire state. And then, because I mean, this is a public algorithm, and, you know, Twist isn't doing some magic. Like we know what it is. It's deterministic. Like if you start out with this state array and you twist it, like at that point, basically, what I'm trying to say is basically, if you know the internal state of the of this random number generator, you can exactly predict every future number it's ever going to give you. So we're going to create a random number generator, and then we're going to run it 624 times to be able to recreate the entire state, and then we'll be able to clone it, and then from that point on, we'll be able to tell with our cloned version what the genuine original version is going to output. So basically, what we need to learn how to do is reverse these operations, and we're going to do it in reverse order. Like, it's going to give us some number, and then we go backwards. So we're going to invert this, then invert that, then so we'll do it in backwards order. Now, I'm trying to think how to explain this because I kind of know how to do it, but let me get my Oh, great, my screen share is not working. Let me pause this for a second and set up my thing. Okay, so here we go. So how to invert, here, let me open so I can read the algorithm at the other window. How are we inverting some of this stuff? So like, let's look at the last one, which is, we'll invert this operation. And how we're going to do that is, so it was, we take some number and then we XOR it with that number shifted by L, which in the case of the 32-bit is 18. So let's call this X. So our goal is to go, actually maybe let's do it this way. Y. So this is the final one where we're going to return. So we'll call this Y1, and we want to get back to the original Y. Like, what did this start out at? So we'll call it Y0. So if you look at kind of an example, there's two different cases here. On one, so we know that whatever Y0 was, we're going to shift it to the right 18 places, XOR it with what the original number was, and then that's going to give us this. So if we look at, let's just take some, I'll do it with 16-bit numbers. Just randomly make some. Okay, so here is some number. We'll say this was what our original number we started out with. So we'll call that, this is what Y0 is. And then there's going to be two different cases. The simplest one is if we shift it more than half the amount. So we've got 16 bits here. Let's say we shift it half or greater. So let's say we're going to shift it to the right. In this example, we're shifting by 9. So what's going to happen to that is everything's going to the right by 9. So that means what we're going to have is 1, 2, 3, 4, 5, 6, 7, 8. Everything after here is going to get dropped off this cliff, and it's going to be all zeros behind here. So we're going to have 0, 1, 1, 1, 0, 1, 1, and then we'll have 9. These aren't lining up well. We'll have 9 zeros. So when we XOR this, so this number here is what this is. This is Y0 shifted by, in our case, 9. And then, whoops. This is our original number. This is our original number shifted by the amount. And what we'll get out, so we're going to XOR these. So XORing is, if they're the same, you get a 0. If they're different, you get a 1. And the beauty of XOR is that anything XORed with 0 is just 0. So if we look where we've got our 9 zeros, because we shifted it over 9, we've already got, like if you look at these 9 bits, it's the 9 bits of the 9 most significant bits of the original number, right? Because nothing changed. We XORed it with all zeros. So our output, Y1, already gives us the first 9 bits of the original number. Well, we know the first 9 bits of the original number, and less than that is what gets left over here, right? Because this is where the number started. So it's the first, 7 bits, because we shifted more than halfway. So we know since we know the first 9 bits and we only need to reconstruct 7, we know what's going to go here, which means we can actually recover this. And the further beauty of that is all we have to do, we can basically do the exact same operation, right? If we know the first 9 here, if we shift this over 9, this 7 here are getting dropped off, as well as these two, which means we'll be left with that right there, which is the exact same thing as that. So all we have to do is shift y1 by 9, and we're going to get the exact same thing, as what this was, right? Because we're going to get 0, 0, 0, 0, 0, 0, 0, 0. We shifted it over 8, 9, and now we're going to get, we're starting from here, so we have 1, 1, 0, 1, 0, 1, 1. And if you look at it, this is exactly the same as that. So all we have to do is repeat the exact same operation, and we get back the original number. So whenever we shift left or right by half or more of the total bits, so if it's like a 32-bit thing, if we shift 16 or more, all we have to do is just repeat the same operation. So we started out with y sub 1 equals y naught XORed with y naught shifted more than half or more. To get y naught, all we have to do is take y1 and XOR it by y1 with the half or more. I'll just put half or more. So like, boom, we undid that one already. Left or right, it's going to be the same way, right? Because if it's here, we knew the most significant bits of the original one. If instead we had shifted to the left, then this number would shift over and it'd be all zeros behind it. So we would actually instead, the same situation, but now we would know the more than half least significant bits of the original number. And it's the exact same thing. When we then shift that this time to the left, we'll know what the most significant bits were, because it's going to be what we knew over here. Now the tricky part is how we handle it when we know less than half, because then we can't do that. But what we can do, here, we'll do the same thing. So we're doing, what do we say? Y1 equals y naught XORed with y shifted to the right. We'll say, so I'll give an example of 16 bits. So let's say we're shifting at 3. Actually, let me do 4. That'll make it one step shorter, I think. So, and we're working on 16. So this is less than half, right? So let me say y0 was equal to, try to space these better this time. 1, 1, 1, 0. All right, so now when we shift to the right, these last 4 bits are going to fall off, and it'll be 4 zeros. So here's y0 shifted to the right by 4. So we know that it's going to be 4 zeros, and then it's just going to be this until we get to the end. So 1, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. And then what do we get? If they're the same, it's a 0. If they're different, it's a 1. 1, 1, 0, 0, 0, 1, 1, 1. And this is what, right? So we would end up, this is what we get back. We know this one. And from that, we have to somehow try and figure out what y0 was. Well, one thing we do know still is we know these 4, it was shifted to the right by 4. So we do know the 4 most significant bits of what the original number was, right? Because we know anything XORed with 0, we know the first 4 bits are all zeros, so we know that Y0 had to start out with the same as what this is here. So we know the first 4 are correct. So we know Y0 actually started out 1, 1, 1, 0. Now we know that when it got, we know it got shifted to the right. We know this amount got shifted to the right. So we know the next 4 bits of what the shift was 1, 1, 1, 1, 0, right? Because we know these 4, it got shifted, so now we actually know those 4. Well, now that we know those 4, we can construct, we can go backwards, right? Because we know these 4 bits came out to this. We don't know what this was. We don't know this. We now know this, and we're given that, so we can just XOR these 2 together to get that. So we can take these 4 bits and XOR them with, I don't know how to write this to make it nice. We can XOR it with the 4 bits we were given. And so now we can, when we XOR those together, right, we get 1101, which, hey, look, that's what the original number was. So now, same thing again, we're just going to like zipper this on down. So it's, now we know what the actual, let me write it here. We know what the first 8 bits of the number were, right? So again, we do the same thing. We know this was the next 4, so when it got shifted, boom, we know that, wait, where was it, 1101? Oh yeah, so we know these were the next 4 bits. And that's what was going to be shifted over. So again, now we know this. We're given this. We can XOR them together to get back to that. So now we can just do the same thing. So we're going to take this one, and we're going to 1, 1, 0, 1. We're going to XOR this. Highlighter here. We're going to XOR these 2. And we get back 0, 1, 0, 0. Which, hey, look, this is exactly what that was. And then we're going to do the same thing again, because now we know the first 12 bits. We know that this is what those next 4 bits were, so shift it over. It was going to be these last 4 bits. We're given that. We do the same thing. So now we'll do just what we did before. So we're XORing, not get lost here, this with this. Let me write this. 1, 1, 1, 0, 1, 1, 0, 1. This is what we know now. Now we're XORing this with 0, 0, 1, 0. We're XORing this with this now, and we get 0, 0, 1, 1, which, hey, look, this is exactly what that is. So now we've recovered the original number, right? This number here is the same as this number here. Yep. So, and it works exactly the same way. We did it on a right shift, but it's going to work exactly the same on a left shift, except we're starting here and kind of working our way down. On a left shift, we'll be starting from the back, because here with the right shift we know the most significant bits and we work our way down. With the left shift we'll know the least significant bits and we'll work our way up, but it's exactly the same. So we're still sleeping over here. So then, like, let's ignore the fact that these ands for a second, because that will. So now we know how to recover the original number from a right shift or a left shift. So if we ignored these, we could build our way back up, right? We know we're returned the lowest W bits. From that, since we know what this was, we could now work our way back up to what this number was, and then we can undo that. We can undo that, we can undo that, and then we're left with the original number. And so we know that's what the state value for that position was. So then we'll be able to reconstruct it. Now, where it gets tricky, or trickier, is normally like in an AND operation, like, let me bring this back up. In an AND, you can't necessarily recover. Like, so let's say here's our original number. Let's just do 8 bits this time. 1 1 0 0 0 1 0 1 0 0 1 1 1 1 1 1, and then we're going to AND it with let's say 1 0 1 1 1 1 1 1 0 1 0 0 0 0 1 1. All right, and this is what we're given. So when we AND these together, we get 1 1 0 0. Right? They both have to be ones in order for us to get a 1. So these are all zeros. 1 0 1 0 0 0 0 1. So we'd know what this was. Or I'll just call this magic number. We're going to know what the mask is, right? Like, it'll be some number we know, and we know the output. But from that, we can't reconstruct what Y0 was. Like, pretend we don't know this. Like, everywhere in the mask, there's a 0. We won't know in the original number if that was a 0 or a 1, because the output will be the same regardless. So everywhere there's a 1, like all these places with a 1, we know those spots in the original had to also be a 1. But everywhere here there's a 0, like we can't tell, we can't reconstruct what the original number was. This stuff could have been like, if say Y0 instead of this was this, we get the exact same thing out. So like you can't go backwards. We would lose that information. But given the fact that they've told us we can go backwards, there must be something about the numbers being used. D, B, C. D was all ones. Okay, so B has 7 zeros at the end. And if we look at C, C is 16 zeros at the end. So that would definitely help us. Oh wait, no, actually it wouldn't. Why can't we recover these? Because we're shifting, ANDing. Oh, this is a shift. Okay, so if it was Y XORed with that and then ANDed, we'd be screwed. But because it's that shifted, masked, and then XORed, we can recover it. Because then basically we'll do the exact same thing. It doesn't really change anything because we know we can reconstruct what these were, right? Because we'll know the valid bits. So then when there's shift, we know those bits, and then we'll be able to AND it with that. Because I'm trying to figure out how to say this here. Like how I showed in the operations where like, we knew what the most significant bits were, and then like we worked our way down. We'll still be able to do that because we know what those bits are. We know they're shifted, and then we know what the mask is, so we can still recover the original. So as we recover more, then it doesn't matter. We'll know what's being ANDed together, which means we can still get the original. It's not the case where we don't know anything about the original and we're ANDing. Here, like if say we knew the first 4 bits here, we'd be able to recover the first 4 bits here. So like, since we know stuff now, we'll know what it's being ANDed with, and that's why we can reverse it. Hopefully that makes sense. Oh no! Our thing did not work. RNG is not defined. Damn it. Line, what is it? Line 37. Son of a bitch. I wonder if anyone, well, I wonder if anyone ever watches these. But I wonder if anyone ever watches it and then like the whole time saw that mistake I made and it was just like, it's not going to work, you idiot. Well, let's YOLO this shit again. All right, so anyway, now we're going to code up challenge 23, and we're basically going to, we'll write a invert right transform, invert left transform, and then we'll give it, since we're going to do it so it'll work with the 64 or 32-bit versions, we'll go ahead, well, I guess we only need to know the shift, so yeah. And then that's the lowest W bit, so we'll have to make a little bit of care to do these correctly to have it work for both. So let me, I'm going to open up, I'm just going to open this up in a browser that I can see so I don't have to switch back and forth. I still have it over here. Oh, no, don't disappear. So we're going to have our, well, first off, let's do a couple imports. We know we need our MT19937. And then, well, let's just do if. Whoa. Okay. So we're going to have an untemper function, right? Untemper, where we're given an original value. So we're given y1, which is an int, and we want to go back to y2. And let me just do this right now, and I think I'll have to add more because I want to make it so that it works for 32 and 64. So I think we're gonna have to pass in the constants. So like if we look at, I'll go show it. If we look at here, so we're tempering. They're calling this tempering. The tempering function is invertible. So this here is the tempering. So we're gonna work backwards. So we're going to on right shift with this, on right shift or on left shift with that, and that masks. So basically I'm just trying to say we're working our way back up. So in here we'll have two other functions: invert right transform. I'll worry about the variables in a minute. And then we'll have invert left transform. And in both cases, they're going to return an integer. And all right, and we know that we're going to want to have, when we invert it, we're going to give it y1 a shift amount and a mask. So the same thing here. Okay, so now we're going to work up backwards. So the first thing we're going to do is well, we know we're eventually going to return what we're going to call y0. And we are going to say, well, here, let's do we know the easy case, right? If shift is greater than equal to, oops. size. Or how do we do most? Oh, so it'll depend because in the 16 or in the 32-bit version. So here, yeah, let's pass in. Let's pass in some constants. So our word size. Probably just maybe I should just call it W. W equals const W. I don't know. I feel like in my head I should call it size so we just don't get us confused. I don't know. I should just use W. So if we know. Actually, maybe I should just. Oh, I'm doing this in the wrong one anyway. We're working. Oh, I'm thinking already. Okay, hold on. I gotta back it up here. All we're doing right now in this function is reversing these. So all we're really gonna do is we are going to invert. Let's see. The first one was a right transform, so we're going to invert right transform. Y. Yeah, let me just call it Y every time. I'll do that. I'll do Y0 and Y1 and the other ones. So we're going to, and it was shifted by, shift is what we have next in shift mask. It was shifted by L. And there is no mask, so we should make a mask optional. I'll just make it nothing for right now. I think what I want to make it is the word size -1, so it's all ones. That way, right? Because in this case, there is no mask. If we still went ahead and ANDed it, because in our transforms, we're going to have ANDs. So if we ANDed it with all ones, it's the effect of basically just keeping that number. Hopefully that kind of makes sense. And then, yeah, that's all we need. Oh wait, no, we need the mask. So we're just not going to pass in a mask. Oh, but we'll need to know the size based on whether or not we're more than half shifting right left. So we do need to know a size. So let's I have a size. Oops. Int. Oh my gosh, my brain's getting fried. Okay, so we're gonna invert a right transform that's by L. So let's just say that size equals const W. I'll just leave it as size instead of word size. Okay, then the next step, we are going to invert a left transform that was shifted by T and ANDed with C. So invert left transform. Our previous one shifted by T, and the mask, well, first we have size, and then the mask is C. And then we're going to undo a left shift by S. Invert left transform Y. it is S. And B. And then now we're going to undo a right transform. Y shifted by U. And D. D. Do what I say. And then we return Y. And then actually, we're going to want to AND this, right? Because, and I'm not sure, maybe this isn't the case, but I'm thinking in my head, we're doing all this shifting and stuff, so we could potentially end up with a number that is much bigger than, like these, say we're in the case of 32-bit. We could end up, if we undo these, maybe we have some number that's like, I don't know, 70 bits or whatever, but we only want 32 because we know the original state, like our state values, you know, our state values are only 32-bit values. So let's just go ahead and AND it by so that's basically the same thing as like how we did here, right? We wanted the, where was it? Where we were at? So we wanted the lowest W bits. So we went 1, shifted it, W amount. So it was 1, and then W zeros subtracted 1 so that it became W ones. So we're doing the same thing here. We're going to take the lowest, or we're going to take the bits of how big the size should be. So now in here, now we can do where I was talking about, well, first we have to handle the mask. If there is no mask, what is the case where there is no mask? It's just this one time. And so that is going to be the same as if we ANDed it by all ones, right? Because we want to get this number. So any number ANDed with all ones is just itself. So if we don't provide it with a mask, I guess we could just make the mask default to all ones, but we don't know what the size is. So here I could actually make it the mask all ones, or I could handle it in here, or somehow I'd like the default to be all ones, but I need to know the size to make the default here. I'll just do it here. So we'll say mask equals mask. So it'll be whatever it was, unless it's 0. So if this is 0, right, then we'll say it's 2 times the size minus 1. Or 2 times size minus 1. Right, because I want it to be, I guess I could do, I don't know why I suddenly switched to exponentiation when I've been shifting the whole time. So we would say, we'll do it the same as how we did it. 1 shifted by size minus 1. Yeah. I don't think you have to do it. I'll be explicit. So it's either going to be what they gave us, or it will be the number of ones of any value we're working with. We want the same thing for here. Probably we could combine these because I think the logic is all going to be the same. It's just one way we're going one way we're going the other. But whatever. We've come too far. So we know the easy case is if the shift is greater than or equal to half the size, then we just return y1 XORed with y1 shifted and mask, right? Because we know the majority of bits, so we'll know more that fills up everything, so we don't have to, that's why we don't have to worry about these ands. We just keep it how it wants to be. And we're doing the, actually, I should just finish it and then copy and paste if it is all the same. Now we have to handle that kind of like zippering logic. So in a right transform, it's going to be, let's see, the original part we want, so in the right transform, we end up knowing the most significant bits of our, I'm going to go back to this real quick. Maybe I'm over explaining. In a right transform, we knew, oh, that was when we knew more. We knew the first most, like when we right transformed by 4, we knew the 4 most significant bits. So for our y0, we start out knowing those most significant bits. So to get the most significant bits, this is probably not, there's probably a better bitwise way to do this, but let's just do y1 shifted by the size minus the shift, and then we'll take that number and shift it back, size minus shift. So basically what I'm doing, I'm sure there's a better way to do it, but like we're going to take this, shift it all the way over here, so it's all zeros behind it, and so it's just, you know, 1 1 1 0. And then since, or here, sorry, we started out with y1, and we know that these 4 bits are the most significant bits of what y0 actually is. I guess I could, another way you could do it would be to take y1 and I want this all to be zeros. Oh, you could just AND it with you'd have as many ones as you knew there were significant bits and make everything else zeros. But what I'm going to do is just take this, shift it all the way over. So, and then, so basically it makes zeros all the way behind, shifts, so that's all we have left. And then we're going to shift it all the way back so it fills in everything behind it with zeros. So that's what this is doing. We're taking size minus shift. So if we only shifted 4, that means we want to do shift those first 4 significant bits 28, like we want to shift it 28 because it'll shift everything off the end except for those 4. And then now we want to take that and shift it all the way back. And then what we want to do is each time we perform, like, so each time we performed one of these operations, right, we recovered shift amount of bits. Like, so initially we know what the first shift most significant bits are. Then we recover the next shift most, like in this case it's 4, so shift is 4. We knew the first 4, then we recovered the next 4 and the next 4. So each time we kind of do this iteration, we're going to recover 4 more of the actual bits. So we want to make sure to recover as many bits as there are actual bits. So like If we were doing 4 every time and it was 32 bits long, we want to do as many loops as it takes for 4 to be equal than or greater to 32. So we will say since we don't need a variable, we'll say for range. We'll start at shift because we already knew the first shift amount. We're going to go until we get to size, and we're going to jump by shift every single time. Right? And then each time through, we're recovering a little bit more of y0. And what we're recovering is y1 XORed with, oh wait, no. Yeah. So we're taking the original one, or not the original, we're taking y1, like, so we first know this is the first 4, and then that's going to get shifted, so we know what that, we know that was going to be there, so we're XORing it with y1 shifted. So it's y1 hold on, now I'm confused. Okay, y1 is what we are given, and we want to get back to this. We know that that is, and then we know what we're XORing y1 with is what we know of y, okay, what we know of y0 shifted. Yeah, see, shifted 4, shifted 4, shifted 4. So we're XORing y1 with y0 shifted. So it's y0 shifted, and then we have our mask. And so that, again, I don't feel like I've probably explained this well, but the reason we can do this and not have to worry about the mask is because each time we know a little bit more about the actual information. Like the first time through, we know what this is. So we know what this is. So we know the first 4 of this, or the first 8 of this, and we'll know the first 8 of the mask because we're given the mask. So it's okay for us then to do this because we can still work out what this, or so, I keep doing it backwards. Yeah, so we know this and we know the mask, so then it's okay for us, then we can use that and we'll be able, we can work out what that is. Oh, I don't know, hopefully that makes sense. If somehow anyone's watching this and that's like a terrible explanation, like, I don't know, feel free to like leave a comment, ask me any questions. Maybe I'll be able to explain it better, or I'm sure there's probably some actually really excellent blogs. I mean, these challenges have been out forever, and all kinds of people have written blogs and done videos about them. So like, there's probably some really awesome, well explained blog posts that go over like this exact thing. So it might be better than listening to some dumbass ramble about it if like you're not entirely sure why we're doing what we're doing. Now, I don't think I can just straight out copy and paste this because for the right transform, we knew the most significant bits, which is why I just shifted and then shifted back. For the left transform, though, it'll be a little bit different. We are going to know the least significant bits. So let me think how to do this. Oh, hey, look, our time suck worked out. Yay. We're going to want to set y0 at the start to it's y1, and we know, oh, you know what, we could just build it up. So we know the least significant bits of y0, right? On a left transform, this number XORed with this number gives us, oh, I was like, that doesn't work out, but it's because I'm actually, we would want to ignore this because this is a little right shifted. I'm trying to just explain it, but do it on a drawing of what's the opposite, which I'm sure just makes everything more confusing. Basically, we know for whatever y1 is, it was shifted over. So we know y0, the least significant bits. I think, honestly, we can just start it out with making y0 equal to y1, because we know the least significant parts of y0 is y1. And again, this is the opposite, so I shouldn't be showing this because I might just be confusing you. But, and then as we'll build up, y0, initially y0, if we make it y1, like it'll be incorrect for everywhere other than the least significant bits, but who cares, because as we keep going, we're building it up and all this crap gets dropped off or shifted off, pushed out to the end to where we don't need it, so we don't care. So we could actually just make, I think we can just do y0 equals y1, and then we'll do the same thing where each time we recover shift amount more, and then we can say y0 equals y1 XOR. It should be the exact same algorithm, except instead of right shifting, now we're going to left shift. So above we had y0 right shifted, now we'll have y0 left shifted, and did with our mask, and then we will return y0. I think that should work. So if my logic is good and we typed everything correctly, now we should basically just, all we need to do now is have a clone. So like, since we're going to test let's test 32. So let's have do like we did before, where we had past 32 equals, we'll call it test mt19937. We'll test the cloning. We'll give a version, and we'll have past 64 equals test. This time it's 64-bit version. And then we'll do our little output like before, where we'll say performing cloning. And then we'll print 32-bit. Oops. Past if past 2, else failed. And then we print staring at the screen so long my eyes are getting blurry. It's like hard to see. I need to take a break. Why is this not working? Oh, dahoy. Oops. All right, so that looks good. So then we just need a test function. I'll have to have a cloning function too. So test, and what did we give it? We gave it a version, and we're going to return a Boolean. Bool. So we're going to give it a seed. We'll just get some random one that we don't know. Between 1 and however many bits it'll accept. But we don't have random imported. Import random. And then we want a state, because that's what we're going to clone it with. Here, let's write the clone first. So we're going to clone something. Oh, I know what we could do. Just trying to think. Yeah, so in our mt blah 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 function, let's actually make where should I put them? Let's do it. We'll have a get state and set state. Def get state self, and return a list of ints. That'll be the state, and it'll just return. I don't think we need to have a get state, but we definitely want a set state, because that's how we're going to clone it. So we might as well have a get state too. Set state self, and it's going to take a state that is a list of ints, and that's not going to return anything. It's just going to change the state. So let's do a little type checking. If the length of the state is not, what was it, in, then you be screwing up somehow, so we'll throw an error. State needs to be of size self in. And then we'll just say, how do we handle where the index is? There's probably a better way to do it, but for this challenge, it's having us tap the whole thing. So we'll set the index to the last value, and then we'll just set the state to the state we pass in, so that automatically the next time you call it, it's going to get twisted. Otherwise, actually, you might not even need the index. It wouldn't matter, right? Oh, you'd want, I'm trying to think here. What if you cloned and didn't have, yeah, you couldn't clone. You'd have to go to the, because you need all 624. So, or you need the full size of the state. So it's not like you're ever going to be able to clone it and your index is somewhere else. Now you could clone it on a previous one, on a previous 64, like depend how many twists ago, and then set. So you could like twist, like if somehow you found the state out So yeah, I'm not going to screw around with it, but if you were actually going to implement this, there might be better ways to do it where you could set the state at any point in the past. Like say, doesn't matter, maybe now the RNG, you've hacked some service or whatever, or cracked or broken their thing, figured out what their seed was, but you or somehow come up figure out what the state was, like I don't know, 30,000 generations ago. You'd still be, you could get it to catch up to where you are. There might be a better way to handle that, but we're not gonna deal with all that. I want to make sure that doing that did not break our thing in any way. So what was I writing? Oh yeah, we're gonna write a clone. Let's just call it clone T1937. Think how we should do this. Let's give it an RNG, and then we'll just do, oh, you know what? Let's also do that in here, because we don't already have that, right? Let's create a variable also for, actually you could just use W, huh? I was gonna say we should give it a variable for the version, but the version is the same as what W is. So, I mean, maybe it'd be better to do that anyway, because it'd make more sense in yeah, let's just go ahead and do that. I think it'll, I mean, it's basically a waste, but it also sort of feels like it makes more sense. And then in here, we could say, we want to get the constants. Those are going to be is constants 32 if RNG version else constants 64. And then we can just use list comprehension to get the state. So we could say the state is going to be for blank in range, however big it is, right? Because the 64-bit version was 300 something and the 32-bit is 624. We are going to get the RNG gen rand int, but, oh wait, I did that wrong. We want to, what I call it, untemperate. So that'll produce the random integer that we will then reverse. And it'll create state many of them, which we can then make a cloned one, right? So we'll start out with 2197 as a new. We want it to be the same version as the random number generator we're using now. We don't care about what the seed is because we're going to clone its state. So the seed is pointless. And then we will set the state and give it the state. And then we will return cloned. So this function will take a random number generator. Ooh. I wonder how you deal with that. Right, because it has to be, or would it matter? No, it would matter. It has to be, this RNG has to be, have not called anything, right? Because otherwise it would screw up our state. So it has to be at its initial or directly after a twist. So that's something you would somehow have to try and figure out if you were actually trying to like attack one where you don't. I wonder what you would do, how you could figure out. You'd have to know how many times it was called. I don't know, there might be some big brain way to do it. But here we don't care because we get to control that. So we're going to have our seed that we don't even know what it is. We'll create, depending what version, and we'll give it that random seed. I should have just stuck rand range in there, but whatever. Then we're going to clone it. Equals giving it our RNG. And then let's test a let's do like how we did other with 1,000 of them. That way at least go through one twist. If cloned gen rand int ain't the same as the original gen rand int, then we be failing. If we make it through all of that, we be passing. All right, well, should be everything, I think. I don't think the odds are good, but let's see. What challenge is this? 23? Oh. No, which I knew I spelled Constance. What did I call it? Constance. Those look the same to me. Oh man, I don't even see what the difference is. Oh, there was definitely. What is going on? My eyes are freaking out on me. Constance. This way was con. Now I can't. Oh, my brain is so fried right now. I can't even remember how you're supposed to spell Constance. Constance, or is it Cont? No, yes, Constance. Dumb. I definitely need a break though. No, I just fixed it. Or did I? What the f is going on? Man, I don't. Constant. No, it's Constance. This is embarrassing. What? All right, if it does it again, I'm gonna throw some shit. God damn it. Constance. I just fixed it. Oh, did I? Oh my God. Constance. I can't. All right, my brain is broken. I can't. Constant. It's like, you know when you like stare at yourself in the mirror for so long that like your face just looks weird to you. Constant. That's how I feel about this freaking word right now. Oh my God. Okay, hold on. Let me Google how to freaking constants and variables. See, it even knows that I want to. And then we're gonna watch. That's one of the reasons why I wanted to do these videos too, is because like I know no one's gonna watch these, so no one's gonna see how embarrassingly bad this is, but good Lord. And if this isn't proof that you can't sit somewhere for hours and your brain doesn't go to crap, then I don't know what is. Oh my God. All right, I don't care. Whatever this is what is getting pasted in here. And if those don't match, I don't, like, there's nowhere else in this file I use it. Did I use it somewhere else in here and I'm not? No, it's the only place. I've saved that. Running that. Okay, hold on. 103, line 103. Oh, I must have it down here somewhere screwed up too. Yeah. I don't even know if I'm spelling it right now. I don't even care. I'm just gonna make sure they're all the same. And okay, whew. Untumper. Line 37. Untemper. Okay, let's see. We must have some. Let's go over these transformy stuffs. We must have something. Let me look at my algorithm. Where's the Wikipedia? Okay. So we're inverting right. That's L size. We're inverting left, T and C. We're inverting left, S and B. We're inverting right, U and D. We return that. Okay. Our mask is 1 is shifted by the size. That should be right. If shift, yeah, we have the shift is greater than 2. We just take it, we shift it to the right and mask, that's fine. So we shift it over size and then we shifted it right back. Maybe it's what I did there. Maybe we can't do y1 equals. We run shift, size, shift. And am I getting size correctly? Yeah, size is the W. Where was I? We shift to the right by mask, or and mask. We return that. If we have the same thing here. Oh, that's what I did wrong. Just because I copied and pasted. Son of a... want to go to the left. Oh, I did say it right. All right, well, that definitely was wrong. So we did at least fix one thing. And then here, this is the one I'm wondering about now, if maybe my logic was wrong. Y0 equals... Well, I don't know. I feel like that should work though, because this is effectively going to be the same thing. Oh, maybe not. Maybe it screws something. So we want the least significant bits of y1. So we could just say y1, and we want the least significant shift bits, right? So that would be the least significant shift bits. This one. It should be that. Maybe that does matter. Like maybe the stuff out in front does screw something up, but I don't feel like it should because we're just pushing that junk off. Are we returning? Yeah, we're returning that. Original is going to be that XORed with shift. Oh. Ooh, okay, hold on. So this definitely is wrong. We wanted to AND, not XOR. So let me change that. Maybe this still works. And what we got wrong was, in fact, this should be an AND and not an XOR. Yeah. Actually, we don't even need that line at all, do we, right? Because we'd set it there. YO equals. Yeah, no, actually, we do need that line. Because that's how you get the first 4 bits. Okay, so that was right. We just had a couple typos. My eyes can't see and my brain stopped working, so I don't know how to spell constants. But other than that, like, I'm actually pretty pleased. Like, and every time we run it, we're getting a different seed because we're just randomly generating one. So, all right, I'm pretty pleased with that. Okay, so we have one challenge. I think we have one challenge left. I can find it. Okay, so I've been stopping these every time after I complete one because I'm worried like I'm going to lose power again or something and I'll lose all that. And I have no idea what I did. But yeah, I've already done this once now and somehow didn't record the audio. So on the plus side, I guess it means I've written the code. So I know it's all going to work. But now I get to like, redo it again. So that's kind of annoying. Anyway, so yay, challenge 24. Let's see what this one's all about. I have no idea. So basically we're going to create a stream cipher out of our random number generator, and it's going to be kind of just like the CTR, right? So in CTR, remember, we generated a key stream, and the key stream is what we used to XOR with plain text or ciphertext, depending on whether we were encrypting or decrypting. We're going to do the same thing now, except we're going to use our random number generator to create a key stream. So we're just going to, whatever random numbers it generates will be the bytes of our key stream. And we're going to make a stream cipher out of that. And then what it's going to have us do is have a message encrypted, and it's going to prepend some random amount of stuff in front of it, and then we're going to break it. I don't know, this exercise kind of seems pointless because really it just seems like it's showing us that a 16-bit seed is way too small, but I kind of feel like we sort of really kind of touched on that in the earlier one. And then this one here is basically the same thing, except now we're just same thing that we did earlier, but we're now just we're doing the same thing, right? We're trying to check to see if this seed comes from the current time. So I don't know. Maybe the point of all this is just to show us that like we can make a stream cipher various different ways. I don't know. But yeah, whatever. Let's jump into it. So what I did and am going to do is we're going to make this a class. Now, we're not ever going to use it again or do anything in other challenges with it, I'm pretty sure. But like, it's just good practice. Like, why wouldn't we make this into something that we can, I don't know, reuse or call later or do whatever, as opposed to just a bunch of functions. So we are making it a class. And we're going to want a version because we're, again, like we've done so far, why quit now? We've made it work, all our stuff work with the 32 or the 64-bit version of the MT19937. So let's keep that up. And we'll have a key. And we're just going to do our version checking in here. We're not going to do like how we did before where we'll create a new one because, I don't know, there's not, doesn't make sense really for what we're doing here. Oops. Now, assuming I can type everything correctly, this should be like, for the video, a no error run. Because like I said, I've got the written code off to the side. I can just look at it. So we're going to throw a value error if it's not one of those versions, and we'll say version must be 32 or 64-bit. And then we'll have our class variables. So we'll have the instance of I guess I should import stuff. Not that it matters since I'm not really using an ID. Oops. So we're going to use our AMT thingy. We're going to need to be doing some XORing. So we're using XOR. We're going to call urandom at some point. Spoiler alert. And then we're also going to use hashlib. SHA-256. We're going to use this for our kind of cheesy little password reset token. And then we're going to import random and time. And here we're going to have something. Oh, I could rename it. I didn't like the name I picked for this the first time around. Basically, since we're doing the 16 or 24-bit version, or sorry, 32 or 64-bit version, each number is going to, like in the 64-bit version, each random int we generate will generate 8 bytes of keystream, and the other one will only do 4. So we need a way to keep track of that. And earlier I called it number of stream bytes, but I ended up not liking that later on. So now let's just call it, I don't know, num bytes. I don't like that either. And basically, that's just going to be our version divided by 8, floor divided, so it's an integer. Although I guess it doesn't really matter for what we're using it for. And then, just like CTR, we are going to do it where once you've encrypted, you can't decrypt. Once you've decrypted, you can't encrypt. So we'll have class variables for can encrypt and can decrypt. There we go. And then we just have our main function, or our two functions. We're going to have self, where we encrypt something, and like always, we're doing bytes to bytes. And then we're going to have our decrypt, where we're doing bytes. Can never hit the, there we go. bytes. So we need to check our, see if we're allowed to encrypt. If we can encrypt, or wait, no. I just look at my code. Yeah, if we can't encrypt, then we throw a type error that says encrypt cannot be called after decrypt. And otherwise we're good, but we need to make sure and now change our can decrypt variable to false, because we are no longer allowed to decrypt. Then, so what we're going to do, since this is a key stream, we're not doing a block, so we need to make sure we at least generate enough key stream in order to have enough key stream available to XOR with the plain text bytes. So I was actually thinking, I guess it doesn't really matter, but I was just thinking about, like, they're not gonna actually come out, like we can have situations where our key stream is a bit longer than what we encrypted, and that could screw things up depending on how you encrypt, because then you have to encrypt the same way. I don't know. So it would probably be better if I somehow thought of some way to make sure we get exactly the amount of bytes we have, like turning each int instead of just shoving it straight into the number of bytes it is, mapping it so that each call to the generate int just generates a single byte. I don't know, I didn't think of that before, but it doesn't, I don't know. That's more complex than we need to worry about it. But if you were actually going to somehow, don't do this, turn this random number generator into a stream cipher for use in some kind of, I don't know, meaningful environment, don't do that. You would definitely want to probably do what I just mentioned. Anyway, so we want to know how many integers we need to generate. And so what we're just going to do is we're going to floor or ceiling divide here, I'll do it out this way. We're going to ceiling divide the length of the plain text by the number of bytes each integer is. And remember, like I kind of talked about this in, I don't remember which video, but we're going to do our ceiling divide. Here, I'll leave a note to ceil divide. This ceiling division, so we're floor dividing with a negative number, so it goes to the next biggest negative number, and then we invert that. So it's basically dividing, but going to, so it's upside down floor division, so it's going to the next biggest positive number, so it's actually ceiling division. And then what we're going to have is our key stream, which is equal to, we're going to generate a list comprehension of our random number generator, where we are generating a rand int, converting that to bytes, right? Because our random number we're generating, say it generates, 74. That's only 7 bytes to make, but we actually want, or 7 bits to make, and we want every number we generate, say if we're in 32-bit, we want it to make 4 bytes out of that. So we're going to convert it to bytes and use the number of bytes and do it big endian. Actually, I think I can leave that out and it'll automatically convert it to big endian. But whatever. You know what? Let's do that. Let's YOLO that and see if It'll be exciting now when I run it to see if we get an error or not. Because I honestly don't know. I think you don't need to specify, and the default is big. Anyway, so range number of generates. So yeah, so I mean I copied it verbatim, so this should be right. But yeah, sure. Seems like it's right. It worked before. It's just kind of hard now that I'm like sort of writing exactly what I'm looking at. It's like I'm not thinking about it as much, so I feel like I might make some stupid mistake. So we're going to XOR that key stream with whatever the plain text is, and since the key stream could potentially be longer than the plain text, we want to make sure, and with our XOR function, just XOR the minimum amount, so whichever one's smaller. Well, it'll always be the key stream. Or I mean, it'll always be the plain text, so they're the same size, or the plain text is smaller. So our decrypt is basically the exact same thing, because that's kind of how stream cipher is. When you're just XORing things, you're generating the key stream, and so encryption and decryption is just XORing, and as we've seen, and the other challenge is like it's the same thing. It's just depending what you're XORing together. So if we can't decrypt, then we are going to raise a type error that says decrypt cannot be called after encrypt. And then otherwise we'll make sure and change can encrypt. No, we are no longer allowed to encrypt. And then we're going to do, let's copy and paste, which we'll see if that makes us fraught with errors. So the only thing I should have to change is PTs into CTs. And that there should be our working stream cipher implemented from the Mersenne Twister random number generator. Oh, did I rewrite that? Ah. And then what I did was, of our if name and main, and we'll have our main, and then I rambled on for a while about why it's dumb to have 16-bit seeds, and then I wrote this function aptly named poorly seeded cipher. And it takes a message in bytes, and it's going to return, I did an integer, or a tuple of bytes. We're going to return the seed as well as the message, and we're just returning the seed so that we can check to make sure we actually cracked it correctly. Like if somehow you were obviously making some kind of service that did this, you wouldn't want to give them the seed. It's really tempting just to copy paste all this. But stylistically, that would just ruin the whole. I should have just acted like I never did any of these. Anyway, so what I'm doing here is, so get ran bits from the random thing will generate a number that is up to that many bits long. And the reason I'm using 12 is because if we do 16, like to brute force, because that's what we're just going to do, is we're going to brute force the seed. To brute force the 16-bit seed could take a couple minutes, and you know, no one wants to just sit there and stare at my console to see if it works. So we're going to do 12 because that will only take a couple seconds. But if you want to do the 16, because that's how they did it in the challenge, like obviously change it to 16. But I'm just doing 12 because these videos are already long enough. And then we're taking our stream cipher, and we're going to do the 32-bit version and with the seed. And then our plain text is going to be, we're going to add in the front of it some number of random bytes between 4 and 42 long, and then we'll concatenate our message to that. And this is kind of the other reason I think it was dumb. Like, well, not dumb, but we're not exactly providing some challenge here. The fact that we're prepending some random amount in front of it, because we know what the message is. So we know how many bytes long it is. We just compare the two, and then we'll know exactly how many bytes of random padding it added. Where was I? So, oh yeah, and then we're going to return the seed and the encryption of our plain text. Then we're going to write this snazzy crack poorly seeded cipher function that we're going to pass ciphertext, the original message, and it is going to give us back the seed. So what we're going to do is just what I said, is we're going to figure out the pad length, and that is going to be the length of the ciphertext minus the length of the message. And then in our message that we're going to try, so basically, here, let me write it and then I'll explain it. We're going to prepend, we can pick whatever, I'm just using P because it stands for pad. We're not going to know what the padding was, so we can't just directly compare the ciphertext they gave us with the ones we're trying to brute force, because we don't know what the padding is, but we need to put padding so that the message lines up with what it would be. So essentially, we're just ignoring whatever the front part is, and we're going to compare the part of the part of the ciphertext we keep generating until we find one that matches the part of the ciphertext that the one that we don't know, like the service or whatever, generated, if that makes sense. So we did a little print statement so that we could tell it was doing something. And then we just basically started brute forcing. So for seed in range, we'll brute force the entire key space. Our test ciphertext equaled the stream cipher, 32-bit with the seed we're currently testing, and we're going to encrypt our prepended. And then what we're going to do is check to see if the test ciphertext starting at the pad length is I don't know why I typed two of those, is equal to the actual ciphertext starting at the pad length, right? Because we don't care about the step before. It's not going to match because we don't know what it was, so we can't feed it the same bytes. We're just checking the part we do know. And if those are equal, then we're going to return the seed. And if somehow we run through all of that and don't get it, we'll just return -1. And then that right there, bam, was everything we need to do the first part of what they said. So we went ahead and tested it here. We generated 14 A's just like they did. And then we ran that through our poorly seeded cipher function. And then we tried to crack that. And then we did our standard. Did we crack it? Well, let's check if the seed is equal to what we cracked. And then we just went ahead and printed these out for some reason. And then we went ahead and ran that. And I can't type. What did I do wrong here? I'm going to set the stack trace. I don't know. Here, let's do it here because I can always read these better. Boolean object is not callable. Line 44. What? Cipher? Oh. Auto-completing and probably staring at the code I already wrote. Man, I'm doing worse now that I've already done it. Invalid syntax, line 64. Is it just I had some kind of weird... Nope. Oh, what? Oh, I somehow... What the heck? I did something really weird. Oh, I must accidentally... I don't know what I did. How did I manage that? Let's go back and watch my own video. Oh, I wonder, because all I did was just erase what I had already written in here. Maybe I didn't erase it all. I don't know. It's a mystery. I'm going to go back and watch my own video just to see how I managed to do that. Oh, now we're going to have all kinds of stupid indent problems. Oh, there's more of it. What? All right, I got to pay attention. Okay, so you do need by order. All right, sweet. Good knowledge to know. So we were doomed to error anyway. Oh, you got to do it in both of them, huh? And it should have already cracked it, which, oh, I never decremented the seed. No, I did. It just took, huh. Like even with the 3900, that took longer than it was earlier. I guess my computer's tired of me talking as well. So yeah, there we go. So that's, again, just a 12-bit. So 16-bit would be a number up to 65,538, I believe. So you can see we did 4,000. We searched 4,000 in a few seconds. So, you know, you do the math, it's not that much longer. And then what we're going to do for this kind of generate, so it's just asking us basically to set some kind of like password reset token and then test whether or not it was seeded with the current time. So we wrote a function where we're going to generate a reset token, and basically we just get a key stream, and we're going to just use the key stream it generates, the cipher generates. We're giving it the seed of time, and we're going to encrypt it with 32 bytes of nothing. So remember, when you XOR anything with 0, you get itself. So we're just getting the first 32 bytes of key stream. And then what we did was, for fun, we SHA-256'd it, and that will be what our reset token is. So it'll be some long hex value that you put in the little address bar, and then basically we just did the same thing as we did in the previous challenge, where we're going to check and see if it's a time seeded token. So we're going to give it the token, which is a string, and we're just going to return whether or not it is the time. So we're going to start at the current time and go down. And then while seed now really you'd know, so like I think I talked about earlier, Unix time is 31 bits, so you wouldn't want to actually run all the way down to 0, because that would take a long time. But I figured I'd put that instead of just while true. And then, so the thing is, like, we need to know, like, somehow we need to know what they were SHA-256ing to get that thing. So not only, what I'm trying to say is we can't just start checking everything to see if, like, hey, let's just go around and see if there's anything on the internet using this stream cipher to generate password reset tokens, because you still need to know what value it is they're actually, like, if they were hashing something to get the password reset token, you still need to know what they are hashing. But if you did find that out, then you could start testing stuff. So basically, we're just going to test if the hex digers, if the hex digest of what we just did is equal to the token. And if it is, then we're going to return true, because that meant, yep, it was seeded with the time. Otherwise, we're going to decrement the seed. And if somehow we're still around when it goes through all 31 bits, it'll tell us, no, couldn't have been a time seed, because and then I'm going to cheat. Then we tested that with, oh, hey, look, I wrote that really quick. We're just getting a reset token. We're going to print that we're testing the token. Then we are printing the token and whether or not it was generated with the current time. And then it cracked that. Then it said that was the token, and it was generated with current time. Yep. So hopefully the audio worked on this one. And yeah, so that's the last challenge. I mean, I pretty much doubt anyone probably ever hears this anyway, but like, hopefully, if you went through these and you saw something and somehow you also are listening to the end of the video, like, I hope you got something out of it. And if somehow you are listening to this, like, I really appreciate it. Like, I don't know, I hope it helped you. And yeah, that's it. I'll be doing the rest of them. So stay tuned, I guess.